Subscribe so you don't miss out on any of these videos. Imagine a structure so massive it spans billions of light years, defying physics and reshaping our understanding of the cosmos. This is the Hercules-Corona Borealis Great Wall, one of space's greatest mysteries. The universe is vast beyond human comprehension, a seemingly infinite expanse filled with cosmic wonders that defy our understanding. But among all the strange and mysterious phenomena in the cosmos, there are structures so enormous that they challenge the very foundations of physics itself. These are the largest galactic structures ever discovered, massive cosmic formations stretching billions of light years across, dwarfing even the most powerful galaxies and clusters. And among them, one stands as the largest of all, the Hercules-Corona Borealis Great Wall. This structure is so unimaginably vast that it shouldn't even exist according to our current understanding of cosmology. It defies the cosmological principle, the idea that, on large scales, the universe should appear uniform in all directions. Yet there it is, stretching across the fabric of space like an immense cosmic scar, forcing us to rethink everything we thought we knew about the limits of cosmic structure formation. Discovered in 2013 through an extensive survey of gamma-ray bursts, the Hercules-Corona Borealis Great Wall is estimated to be around 10 billion light-years across. That's over 10% of the observable universe's diameter. To put that in perspective, if you traveled at the speed of light from one end to the other, it would take you 10 billion years, longer than the Earth has even existed. This staggering scale makes it the largest known structure in the universe, surpassing even other colossal formations like the Sloan Great Wall, the CFA2 Great Wall, and the Laniakea supercluster. But how did such an immense formation come to exist? And why is it such a fundamental problem for modern astrophysics? The existence of such a massive structure presents a direct challenge to one of the key principles of modern cosmology, the idea that the universe is homogeneous and isotropic on large scales. This assumption, known as the cosmological principle, states that when you zoom out far enough, the distribution of matter in the universe should appear roughly uniform. But the Hercules-Corona Borealis Great Wall defies this expectation. According to the standard lambda cold dark matter model of cosmology, structures larger than 1.2 billion light-years shouldn't be able to exist, as gravity and the expansion of the universe wouldn't allow matter to clump together on such an enormous scale. Yet, this colossal structure not only exists but appears to be a coherent formation of galaxies and matter extending across a mind-boggling portion of the observable universe. To understand how scientists even discovered something so immense, we need to look at the methods used to map large-scale structures in the cosmos. Traditional galaxy surveys help us map out clusters and walls of galaxies, but for something as vast as the Hercules-Corona Borealis Great Wall, astronomers turn to gamma-ray bursts. These are some of the most powerful explosions in the universe, caused by massive stars collapsing into black holes. Because they shine across vast cosmic distances, gamma-ray bursts serve as excellent markers for tracing the distribution of matter in the distant universe. When researchers analyzed the locations of gamma-ray bursts over time, they noticed something unusual, a massive concentration of these events spanning an enormous region of space. The pattern suggested that they were occurring within a vast interconnected structure, revealing what we now call the Hercules-Corona Borealis Great Wall. But how could such a structure have formed? Current theories of structure formation in the universe revolve around the influence of dark matter and the gradual gravitational clumping of smaller structures into larger ones. Galaxies are not randomly scattered throughout space. They form along massive filaments of dark matter, which create a vast cosmic web. Over billions of years, these filaments pull matter into larger superclusters, creating immense structures such as the Sloan Great Wall and the CFA2 Great Wall. However, even these pale in comparison to the Hercules-Corona Borealis Great Wall. Its sheer size suggests that some unknown force or mechanism must have influenced its formation, as the timescales involved in its growth defy conventional models. One possibility is that the structure formed in the early universe when density fluctuations in the cosmic microwave background created the seeds of massive structures. If this is the case, it would suggest that these fluctuations were much larger than previously thought, potentially requiring revisions to our models of cosmic inflation, the rapid expansion that occurred fractions of a second after the Big Bang. Alternatively, it could suggest that some unknown form of interaction between dark matter and normal matter allowed such a structure to grow far beyond the expected limits. Another possibility is that the Hercules-Corona Borealis Great Wall isn't a single cohesive structure in the way we imagine it. Instead, it could be a vast network of galaxy clusters and filaments that just happen to be aligned in a way that makes them appear as one massive entity. However, this explanation raises more questions than answers, as the probability of such an alignment occurring purely by chance is extremely low. If anything, the structure's existence suggests that our understanding of the large-scale universe is incomplete, hinting at unknown forces or hidden properties of dark matter that we have yet to uncover. The implications of this discovery extend far beyond just astrophysics. If structures like this can exist, it may mean that the very fabric of the cosmos is organized in a way we don't yet fully understand. It challenges the fundamental assumptions of how matter is distributed across the universe, and by extension, how the universe itself evolved over time. Some scientists even speculate that the existence of such a massive structure could point to unknown physical laws governing cosmic structure formation, or perhaps even interactions between universes in a multiverse scenario. Even more intriguingly, the Hercules-Corona Borealis Great Wall may not be the only structure of its kind. Given that we are constantly refining our observational techniques and uncovering new cosmic formations, it's possible that even larger structures remain hidden beyond our current reach. If astronomers discover another similarly vast structure, it would all but confirm that something fundamental about our cosmological models is missing. Despite its staggering size, the Hercules-Corona Borealis Great Wall remains largely mysterious. We still don't fully understand how such a massive structure could have formed, and its discovery raises deep questions about the limits of cosmic structure formation. It serves as a reminder that the universe is far more complex and enigmatic than we ever imagined, and that our best theories may only be scratching the surface of its true nature. The more we look into the vastness of space, the more we realize that there are still cosmic mysteries waiting to be uncovered, mysteries that could one day reshape our entire understanding of reality itself. If the Hercules-Corona Borealis Great Wall truly represents a coherent large-scale structure, then its very existence forces us to rethink some of the most fundamental ideas in cosmology. The challenge is not just its size but the implications of such a massive formation existing in a universe that, according to the Standard Model, should not allow it. The cosmic web, which is the large-scale structure of the universe, consists of galaxies and clusters strung along filaments of dark matter. These filaments intersect in dense nodes, forming superclusters, while vast cosmic voids separate them. But even the largest superclusters and walls observed before this discovery were within theoretical limits, until now. The Hercules-Corona Borealis Great Wall spans about 10 billion light-years, meaning that light from one end of the structure would take longer to reach us than most of the galaxies we observe. This also suggests that the structure formed very early in the universe's history, at a time when matter was still settling into its large-scale distribution. Given that the universe is estimated to be about 13.8 billion years old, a structure of this scale forming so soon presents serious problems. Cosmologists use the concept of a correlation length to describe the largest possible structures that could have coalesced under known physics. This correlation length is estimated to be around 1.2 billion light-years, meaning that anything much larger than this shouldn't have had enough time since the Big Bang to form as a single, connected structure. But the Hercules-Corona Borealis Great Wall defies this expectation entirely. One of the biggest mysteries surrounding this structure is its potential influence on the cosmic microwave background, CMB, the faint radiation left over from the Big Bang. Any structure of this size would have a gravitational influence on the surrounding space, which should leave subtle imprints on the CMB. However, when scientists examined the CMB for signs of such an influence, they found little to no direct evidence that the Hercules-Corona Borealis Great Wall is affecting it in the way we would expect. This raises two possibilities: either the structure is much less dense than it appears, or there is something about the nature of large-scale gravitational interactions that we do not yet understand. Another problem arises when considering the dark energy-driven expansion of the universe. As space expands, galaxies and other structures are pulled apart at accelerating rates. The presence of a massive structure like the Hercules-Corona Borealis Great Wall should, in theory, be affected by this expansion. Yet, it appears to have remained coherent over billions of years, suggesting that its gravitational bonds are far stronger than expected. This leads some researchers to question whether dark matter plays an even greater role in large-scale structure formation than previously assumed. Dark matter, an invisible form of matter that interacts only through gravity, is believed to account for most of the mass in the universe. It forms the scaffolding upon which galaxies and superclusters are built. If the Hercules-Corona Borealis Great Wall is truly as vast as it appears, then it must be supported by an equally enormous dark matter framework, one that challenges existing models of how dark matter clumps and behaves over cosmic timescales. This could mean that either dark matter is distributed in a way we don't yet understand, or that some yet undiscovered force is acting upon it to create such a massive structure. One of the more speculative but fascinating possibilities is that the Hercules-Corona Borealis Great Wall is a relic from an earlier phase of the universe, one in which the fundamental laws of physics may have been different. Some cosmologists propose that the early universe underwent multiple phases of cosmic inflation, rapid expansion events that shaped the distribution of matter on the largest scales. If an anomalous inflationary event occurred, it could have created density fluctuations that led to the formation of an unusually massive structure like this one. However, proving such a theory would require detecting specific patterns in the distribution of galaxies or in the cosmic microwave background, something we have yet to achieve. Another radical hypothesis suggests that the structure might not be a true physical entity, but rather an observational artifact caused by an unknown bias in our measurement techniques. Could it be that our method of using gamma-ray bursts to trace cosmic structure is inadvertently creating the illusion of a massive connected structure? While this is unlikely, given the statistical significance of the data, it's not entirely out of the question. If a systematic bias in our observations exists, then we may be overestimating the coherence of the Hercules-Corona Borealis Great Wall, and future surveys with different methods could refine our understanding of its true nature. If the structure is real and as vast as currently estimated, it would force a major revision of the standard model of cosmology. The existence of structures this large suggests that the formation of the universe is governed by principles we do not yet fully understand. One possibility is that our current understanding of cosmic inflation, the rapid expansion of the universe immediately after the Big Bang, may be incomplete. If inflation created larger fluctuations than previously thought, it could explain the existence of superstructures like this. However, modifying inflationary theory is not a simple task, as it would require a delicate balance to still account for the other observed large-scale features of the universe. There is also the question of what this means for the fate of the universe. If structures on the scale of the Hercules-Corona Borealis Great Wall are common, then it could suggest that the universe is far more clumpy than we currently assume. This could have implications for how dark energy behaves over time. Dark energy is the mysterious force driving the acceleration of the universe's expansion, but if its effects are not uniform across all scales, then our predictions for the ultimate fate of the cosmos may need to be revised. Could these massive structures point to something even stranger, such as the existence of hidden dimensions or interactions beyond the four we currently understand? Some theories in physics, such as string theory, propose the existence of extra-spatial dimensions beyond the three we perceive. If these dimensions influence the large-scale structure of the universe in some subtle way, it could provide an explanation for why such immense formations exist. However, this is still purely theoretical, as we currently have no direct evidence for extra dimensions. Regardless of the exact explanation, the discovery of the Hercules-Corona Borealis Great Wall serves as a powerful reminder that the universe is still full of mysteries waiting to be unraveled. It stands as a testament to the fact that, no matter how much we think we understand about the cosmos, there will always be new discoveries that challenge our assumptions and push the boundaries of human knowledge. If further observations confirm its existence and structure, it may go down as one of the most important discoveries in astrophysics, prompting a reevaluation of some of the most fundamental principles in cosmology. And if, in the coming decades, astronomers discover even larger structures, then we may be on the verge of uncovering a hidden aspect of the universe that could redefine our understanding of its origins, evolution, and ultimate destiny. The Hercules-Corona Borealis Great Wall is a cosmic enigma, a structure so vast that it stretches the limits of our comprehension. It forces us to question what we thought was possible in the universe and opens the door to new and exciting scientific possibilities. Whether it is the result of unknown physics, dark matter interactions, or some other force yet to be discovered, one thing is certain: this colossal formation will continue to intrigue and mystify astronomers for generations to come. The implications of the Hercules-Corona Borealis Great Wall stretch far beyond its mere size. If such a vast structure exists, it suggests that our understanding of cosmic evolution is incomplete. The standard model of cosmology is based on the assumption that the universe is homogeneous and isotropic on the largest scales, meaning that, when averaged over great distances, matter should be evenly distributed. However, the presence of such a massive and complex structure contradicts this assumption, raising the question of whether the universe is far more structured and interconnected than we previously believed. This leads to a fascinating debate. Is the Hercules-Corona Borealis Great Wall a statistical outlier, or does it represent an entirely new class of cosmic formations that challenge the fundamental principles of physics? If it is an outlier, then perhaps it is simply a rare event, something that formed due to unique and extreme conditions early in the universe's history. However, if more structures of this scale are found, it could suggest that our current cosmological models need a major overhaul. One of the most striking aspects of the Hercules-Corona Borealis Great Wall is its relation to the concept of the cosmic horizon. The observable universe is limited by the speed of light. We can only see objects whose light has had enough time to reach us since the Big Bang. If the universe is about 13.8 billion years old, then the furthest observable objects are around 46 billion light-years away due to cosmic expansion. The fact that a structure spanning 10 billion light-years exists within this observable universe is mind-boggling. It raises the possibility that even larger structures may exist beyond our visible horizon, structures so immense that we may never detect them directly. If we were to find evidence of even larger formations beyond the Hercules-Corona Borealis Great Wall, it could lead to the idea that the universe is structured in a way we never anticipated. Some cosmologists have speculated that our universe may be part of a much grander cosmic architecture, potentially even a multiverse where regions of vastly different densities and structures exist. Could it be that the Hercules-Corona Borealis Great Wall is merely a small part of an even greater pattern, one that we have yet to fully perceive? One of the biggest challenges in understanding this structure is that we are limited by observational constraints. The primary method used to detect the Hercules-Corona Borealis Great Wall was through gamma-ray bursts, GRBs, which are some of the most energetic explosions in the universe. GRBs serve as cosmic beacons, allowing astronomers to map the distribution of matter in deep space. The discovery of the Great Wall was made when a large clustering of GRBs was detected, suggesting a massive underlying structure of galaxies and dark matter. However, relying on GRBs presents its own set of challenges. Since GRBs are rare, occurring only once every few million years in a given galaxy, the data we have is still somewhat sparse. There is a possibility that more detailed surveys could reveal an even larger extension of the Hercules-Corona Borealis Great Wall, or that future observations could challenge its coherence. Until we have more data from next-generation telescopes and mapping projects, the true nature of this structure remains an open question. The existence of such an immense structure also raises questions about the role of dark matter and dark energy in shaping the cosmos. If the Hercules-Corona Borealis Great Wall is held together by dark matter, then it suggests that dark matter clumps on scales far greater than we previously thought. This could mean that dark matter interacts in ways beyond just gravitational attraction. Perhaps it has subtle properties that allow it to form structures of unimaginable size. Conversely, dark energy, the force driving the accelerated expansion of the universe, should be working against the formation of such structures. Dark energy causes galaxies to move away from each other at increasing speeds, meaning that extremely large structures should be difficult to form and maintain. The fact that the Hercules-Corona Borealis Great Wall has remained intact for billions of years suggests that either dark energy is not as uniform as we assume or that it has only recently begun to dominate cosmic expansion. One of the most radical implications of the Hercules-Corona Borealis Great Wall is the possibility that it could be a remnant of an earlier phase of the universe, one that operated under different physical laws. Some physicists speculate that the fundamental constants of nature, such as the strength of gravity or the properties of dark matter, may have been different in the distant past. If so, then perhaps structures like the Great Wall could have formed in an era when the universe allowed for more extreme clustering of matter. This idea ties into the hypothesis that the universe underwent multiple phases of inflation, brief moments of incredibly rapid expansion that shaped the cosmic landscape. If there were fluctuations in how inflation occurred across different regions, it could explain why some areas of the universe contain impossibly large structures while others remain relatively empty. The Hercules-Corona Borealis Great Wall may be a fossilized remnant of one of these inflationary anomalies, a cosmic signature left behind from a time when the laws of physics behaved differently than they do today. Another intriguing question is whether this structure might hold clues about the ultimate fate of the universe. The Standard Model suggests that the universe is expanding at an accelerating rate due to dark energy. If this continues indefinitely, all galaxies will eventually be pushed so far apart that they become isolated, leading to a cold, dark, and empty cosmos in the distant future. However, if structures like the Hercules-Corona Borealis Great Wall are more common than we think, it could imply that cosmic expansion is not as uniform as we assume. Could it be that massive structures create local gravitational zones that resist expansion? If so, then certain regions of the universe might remain gravitationally bound, preventing them from dispersing completely. This could mean that the universe's fate is not as straightforward as a simple heat-death scenario. Instead, we may find that pockets of the cosmos remain interconnected, potentially allowing for new cosmic cycles to emerge in the distant future. One of the most mind-bending possibilities is that the Hercules-Corona Borealis Great Wall is not just a physical structure but a manifestation of some deeper, hidden order in the fabric of reality. Some theories in physics propose that space-time itself may be structured in ways we do not yet understand. If so, then perhaps these massive cosmic formations are not just randomly assembled clusters of galaxies, but rather expressions of a more fundamental geometric pattern underlying the entire universe. This idea is reminiscent of concepts in quantum gravity, where space-time may emerge from deeper, more fundamental principles. If the distribution of matter on the largest scales follows hidden mathematical patterns, then the Hercules-Corona Borealis Great Wall could be a key to unlocking a deeper layer of reality, one that connects the macroscopic structure of the universe with the strange and counterintuitive world of quantum mechanics. Ultimately, the Hercules-Corona Borealis Great Wall remains one of the most enigmatic discoveries in modern astronomy. Whether it is a statistical fluke, a relic from an unknown phase of the universe, or evidence of new physics, one thing is clear: it forces us to reconsider the limits of what is possible in the cosmos. As our technology improves and our observations become more precise, we may one day uncover the true nature of this massive formation, shedding light on some of the deepest mysteries of existence. Until then, the Hercules-Corona Borealis Great Wall stands as a reminder that the universe is still full of surprises. It challenges us to think bigger, to question our assumptions, and to embrace the unknown. In a cosmos as vast and mysterious as ours, every new discovery brings us closer to answering the ultimate question: what is the true nature of the universe, and what secrets has it yet to reveal? The discovery of the Hercules-Corona Borealis Great Wall also raises profound questions about the limitations of our observational technology. Even with our most advanced telescopes and space-based instruments, we are still only scratching the surface of the vast cosmic web. If this structure is truly as large as the data suggests, it may only be a fragment of an even more colossal network of interconnected galaxies that spans across regions of space we have yet to explore. One of the most exciting developments in modern astronomy is the rise of next-generation telescopes and sky surveys, which will provide us with far more detailed maps of the universe. The Vera C. Rubin Observatory, set to begin operations soon, will conduct the Legacy Survey of Space and Time, LSST, which will revolutionize our ability to detect large-scale structures in deep space. Additionally, the James Webb Space Telescope, JWST, and the upcoming Nancy Grace Roman Space Telescope will allow astronomers to peer deeper into the cosmos than ever before. These instruments will help us determine whether the Hercules-Corona Borealis Great Wall is truly an isolated phenomenon or part of a much larger, interconnected framework of galactic formations. If other, similarly massive structures are discovered, it could force us to completely rethink the fundamental nature of cosmic organization. It may even hint at a deeper, hidden order within the universe, one governed by laws that extend beyond our current understanding of physics. One of the most intriguing aspects of these discoveries is the possibility that the universe itself may possess an underlying fractal-like structure. A fractal is a pattern that repeats at different scales, from the microscopic to the cosmic. Some researchers have suggested that the distribution of galaxies may follow a fractal pattern, meaning that the same clustering principles that apply to small-scale structures, such as stars and star clusters, may also apply on the grandest cosmic scales. If this turns out to be the case, then the Hercules-Corona Borealis Great Wall might be just one manifestation of a much broader fractal-like design that extends across the entire universe. This would have profound implications for cosmology, as it would suggest that the large-scale structure of the universe is not random, but instead follows hidden mathematical principles. Furthermore, the presence of such a massive structure raises fundamental questions about the nature of cosmic inflation. Inflation is the rapid expansion of the universe that took place immediately after the Big Bang, and it is responsible for the large-scale structure we observe today. However, if inflation was completely uniform, we would expect matter to be evenly distributed throughout the cosmos. The existence of a structure as vast as the Hercules-Corona Borealis Great Wall suggests that there were extreme variations in the inflationary process, variations that may have created pockets of the universe with vastly different densities. This idea aligns with some theories of the multiverse, which propose that different regions of the cosmos may have experienced inflation at different rates. If this is true, then the Hercules-Corona Borealis Great Wall may be a relic of a unique inflationary event, one that occurred in a localized region of the universe and led to an unusually dense concentration of galaxies. The implications of this are staggering. It could mean that other regions of the cosmos, far beyond our observable horizon, may contain even larger and more complex structures that we may never be able to detect directly. If the universe is truly infinite, then the possibility of structures even greater than the Hercules-Corona Borealis Great Wall becomes not just a possibility, but an inevitability. This leads to another mind-bending question. Could such massive structures be evidence of an even grander cosmic phenomenon? Some scientists have speculated that the universe may be shaped by forces beyond our current understanding, forces that could be remnants of higher dimensional interactions. If higher dimensions exist, as proposed by string theory, then the structure of our universe may be influenced by hidden variables that we have yet to discover. The idea that our universe is embedded in a higher dimensional space is not as far-fetched as it may seem. Some versions of string theory suggest that our three-dimensional universe is actually a brane, floating in a higher dimensional reality. If this is true, then the distribution of galaxies and cosmic structures may be shaped by interactions with these extra dimensions. The Hercules-Corona Borealis Great Wall could be one such manifestation, a pattern imprinted onto our three-dimensional cosmos by forces originating from a deeper, more fundamental reality. These ideas remain speculative, but they highlight the profound mysteries that still surround the largest structures in the universe. Every time we think we have reached the limits of what is possible in cosmology, the universe surprises us with something even more astonishing. The Hercules-Corona Borealis Great Wall is a perfect example of this, a structure so vast and so unexpected that it forces us to reconsider everything we thought we knew about the cosmos. As we continue to explore the universe, we may eventually uncover even greater cosmic formations, structures so large and so complex that they defy all conventional explanations. The question then becomes, what is the true limit of cosmic structure? How big can the universe's largest formations become? And what forces are responsible for shaping them? Perhaps the answers lie in the fundamental nature of spacetime itself. Some physicists have proposed that spacetime is not a continuous, smooth fabric but instead consists of discrete, fundamental units, similar to how matter is composed of individual atoms. If this is the case, then the arrangement of galaxies on the largest scales may be dictated by the very architecture of spacetime itself. Another possibility is that these massive structures are connected in ways we do not yet understand. Some researchers have explored the idea that cosmic structures may be linked by unseen forces, such as cosmic filaments composed of dark matter. These filaments form the scaffolding upon which galaxies cluster, and they may extend across distances far greater than we previously imagined. If so, then the Hercules-Corona Borealis Great Wall may not be an isolated entity, but rather a part of an even larger, interconnected cosmic network. The more we learn about these enormous formations, the more they challenge our understanding of the universe's origins and its ultimate fate. If structures like the Hercules-Corona Borealis Great Wall continue to form and grow over billions of years, then the large-scale structure of the universe may be far more dynamic than we previously thought. Instead of a universe that slowly expands into a cold and lifeless void, we may be living in a cosmos that is constantly evolving, one where vast, interconnected superstructures emerge and interact over eons. The future of cosmic exploration holds endless possibilities. With new technology, more advanced telescopes, and a deeper understanding of physics, we may one day unlock the true nature of these massive formations. Perhaps we will discover that they are relics from an earlier era of the universe, remnants of a time when the laws of physics were different. Or maybe they are just the tip of the iceberg, the first hints of an even greater cosmic order that extends beyond the limits of human imagination. For now, the Hercules-Corona Borealis Great Wall remains one of the greatest mysteries of the cosmos. It stands as a testament to the scale and grandeur of the universe, a structure so immense that it stretches the boundaries of what we thought was possible. And with each new discovery, we are reminded that the universe is far more complex, far more mysterious, and far more extraordinary than we could ever have imagined. The implications of the Hercules-Corona Borealis Great Wall go beyond mere scale. They challenge the very foundations of our understanding of cosmic structure, physics, and the evolution of the universe. If such a vast structure exists, then our current models of how galaxies form and organize on a grand scale might need to be revised. One of the most fundamental assumptions in modern cosmology is the cosmological principle, which states that the universe, when viewed on sufficiently large scales, is homogeneous and isotropic, meaning that it should look roughly the same in all directions, with no significant variations in density. This assumption underpins the widely accepted lambda cold dark matter model, which describes how the universe evolved from the Big Bang to its present state. However, the discovery of the Hercules-Corona Borealis Great Wall puts this principle into question. If the universe truly adhered to homogeneity on the largest scales, structures of this magnitude should not exist. The lambda cold dark matter model predicts a maximum theoretical size for cosmic structures, beyond which matter should be evenly distributed. Yet, the Hercules-Corona Borealis Great Wall vastly exceeds this expected limit, suggesting that either our understanding of cosmic evolution is incomplete, or that unknown forces are at play in shaping the large-scale structure of the cosmos. One possible explanation for such an anomaly is the existence of cosmic voids, immense regions of space with very few galaxies. These voids could play a role in allowing massive structures like the Hercules-Corona Borealis Great Wall to persist by acting as gravitational wells that help cluster galaxies together. However, even with the influence of these voids, the sheer scale of this structure remains difficult to explain. Another hypothesis is that the Hercules-Corona Borealis Great Wall could be a relic from an earlier phase of the universe, one that predates the formation of modern galaxy clusters. Some researchers have suggested that structures like this could be remnants of primordial density fluctuations, variations in matter distribution that existed shortly after the Big Bang. If these fluctuations were more extreme than previously believed, they could have given rise to vast, interconnected networks of galaxies that remain visible today. Additionally, the presence of such a massive structure raises questions about the influence of dark matter and dark energy on the large-scale distribution of galaxies. Dark matter, which makes up about 27% of the universe, acts as an invisible framework that helps bind galaxies together through its gravitational effects. Dark energy, on the other hand, is responsible for the accelerated expansion of the universe, working against the force of gravity. If dark matter is more clumped or distributed differently than our current models suggest, it could allow for the formation of unusually large structures like the Hercules-Corona Borealis Great Wall. Alternatively, if dark energy is not a uniform force but instead fluctuates across space, it could be influencing the clustering of galaxies in ways we do not yet understand. Some scientists have even speculated that structures of this scale could be evidence of previously unknown cosmic forces or interactions. One radical idea is that the universe might possess a large-scale magnetic field that subtly influences the distribution of galaxies. While no direct evidence for such a field has been found, some observations suggest that magnetic effects could play a role in shaping the cosmic web. Another possibility is that the Hercules-Corona Borealis Great Wall is not merely a passive structure but instead part of a larger dynamic system. In other words, it may not be a static formation, but rather something that evolves over time through interactions with other cosmic structures. If this is the case, it could mean that the large-scale structure of the universe is far more complex and interconnected than we currently believe. This idea aligns with recent discoveries about the motion of galaxies within large structures. Observations have shown that galaxies within superclusters and great walls do not simply drift through space randomly. They move in coordinated, often unexpected ways, suggesting the presence of large-scale gravitational flows that guide their motion. The study of these flows, known as cosmic velocity fields, could provide further insights into how structures like the Hercules-Corona Borealis Great Wall form and evolve. As we continue to develop more advanced observational techniques, we may one day be able to map the true extent of this structure in greater detail. Future radio telescopes, such as the Square Kilometre Array, SKA, will allow us to detect faint radio emissions from distant galaxies, revealing the full extent of their distribution. Similarly, deep space observatories like the Euclid Telescope and the Nancy Grace Roman Space Telescope will provide new insights into the nature of dark matter and its role in shaping cosmic structures. If more structures of this magnitude are discovered, it could lead to a paradigm shift in our understanding of the universe's architecture. We might come to realize that the cosmic web is far more hierarchical and structured than we ever imagined, with great walls and filaments stretching across distances that defy our current models. Another fascinating implication of these discoveries is the potential link between large-scale structures and fundamental physics. Some researchers have suggested that cosmic formations like the Hercules-Corona Borealis Great Wall could provide indirect evidence for modifications to general relativity, or even hints of new physics beyond the standard model. If gravity behaves differently on these immense scales, it could explain how such structures are able to persist without collapsing under their own weight. One particularly intriguing possibility is that these structures are linked to the nature of time itself. Some theoretical physicists have proposed that the universe may contain regions where time flows at different rates due to variations in spacetime curvature. If this is the case, then the Hercules-Corona Borealis Great Wall could be a sign of an ancient cosmic boundary, one where the flow of time was once different from what we observe today. The more we study this structure, the more questions it raises. Is it truly the largest structure in the universe, or are there even greater formations lurking beyond the limits of our observable cosmos? If so, what do these structures tell us about the fundamental nature of reality? Could they be evidence of a deeper order within the universe, one that we have yet to fully comprehend? As technology advances and our ability to explore the cosmos improves, we may one day uncover the full extent of the universe's largest structures. Whether they are relics of the past, active components of a dynamic cosmic system, or evidence of forces beyond our current understanding, they represent one of the greatest mysteries of modern astronomy. For now, the Hercules-Corona Borealis Great Wall stands as a monument to the vastness of the cosmos. It challenges our theories, stretches our imagination, and reminds us that the universe is still filled with wonders we have yet to uncover. Each new discovery brings us one step closer to answering some of the biggest questions in science, questions that may ultimately redefine our place in the cosmos. The mystery of the Hercules-Corona Borealis Great Wall is not just about its size but also about what it represents, an anomaly so vast that it threatens to overturn some of the fundamental principles of cosmology. If this structure is real, then our understanding of how matter is distributed throughout the universe may be incomplete, or worse, incorrect. It could suggest that the forces shaping the universe operate on scales we never anticipated, and it might even hint at unknown physics beyond our current theories. One of the most fascinating aspects of this structure is its apparent connection to gamma-ray bursts, GRBs. The Hercules-Corona Borealis Great Wall was initially detected because of an unusual clustering of these extremely energetic cosmic explosions. GRBs are some of the most powerful events in the universe, produced either by the collapse of massive stars or the mergers of neutron stars and black holes. They release an enormous amount of energy in just a few seconds, often outshining entire galaxies. The discovery of a pattern in GRB distribution that aligns with the Hercules-Corona Borealis Great Wall is highly significant. It suggests that these bursts may be associated with the structure itself, meaning that the galaxies within it could be home to an unusually high number of massive stars that eventually explode as GRBs. This clustering of GRBs raises a profound question. Is there something special about the conditions within the Great Wall that makes such events more likely? One possibility is that the galaxies within this enormous structure formed earlier in cosmic history than those outside of it, leading to a higher concentration of massive stars that are prone to undergoing supernovae and producing gamma-ray bursts. If this is true, then the Hercules-Corona Borealis Great Wall might be a relic of an ancient period of star formation, a vast cosmic nursery where some of the universe's most massive stars were born and died in spectacular fashion. But this explanation is not without its problems. The distribution of GRBs should generally follow the distribution of galaxies across the sky, yet in this case, we see an unexpected concentration within a single enormous region. This could imply that our understanding of how GRBs occur is incomplete, or that unknown factors are influencing their occurrence. Could there be a yet undiscovered cosmic phenomenon at work? Some physicists have speculated that the clustering of GRBs might be linked to large-scale magnetic fields or even exotic new physics. If an unknown force or structure exists on this scale, influencing the birth and death of stars, it could be something completely outside of our current models. Another possibility is that the distribution of GRBs is revealing a deeper, underlying structure of the universe that we have not yet fully grasped. Some theoretical physicists have suggested that space itself might have a kind of texture, at extremely large scales, which could influence where galaxies and cosmic events like GRBs occur. If this is true, then the Hercules-Corona Borealis Great Wall might not be just a collection of galaxies, but a fundamental feature of the universe's large-scale architecture. This leads to another tantalizing question. Could the Hercules-Corona Borealis Great Wall be a sign of something even more extraordinary, such as evidence for the multiverse? Some interpretations of quantum mechanics and string theory suggest that our universe may be just one of many, with large-scale structures like this potentially serving as boundaries between different cosmic regions. If this is the case, the Great Wall might be more than just a gravitationally bound collection of galaxies. It could be a clue to the very nature of reality itself. The idea that such a structure could point toward a deeper understanding of the universe is both exhilarating and daunting. If the Hercules-Corona Borealis Great Wall is real and its size is not an observational illusion, then it means our theories of cosmic structure formation must be revised. It might suggest that the universe is far less uniform than we assumed, or it might indicate that unknown forces or conditions in the early universe allowed such a massive structure to emerge. But as with any extraordinary claim, skepticism is necessary. Some astronomers have pointed out that the detection of such a vast structure might be an artifact of our observational methods rather than a physical reality. Because gamma-ray bursts are detected using telescopes with limited fields of view, it is possible that the apparent clustering of GRBs in this region is due to biases in our data rather than the presence of an actual physical structure. To confirm the existence of the Hercules-Corona Borealis Great Wall, astronomers need more precise measurements and a more comprehensive survey of the sky. Upcoming missions, such as the Vera C. Rubin Observatory and the Euclid Telescope, will help map the large-scale structure of the universe in greater detail than ever before. If these observations confirm the existence of this enormous structure, then we will have no choice but to reconsider some of the most fundamental assumptions about how the universe works. The Hercules-Corona Borealis Great Wall stands as one of the greatest cosmic mysteries of our time. If it truly exists at the scale suggested, it could revolutionize our understanding of the universe's structure, the distribution of matter, and the forces shaping the cosmos. It could challenge the cosmological principle, force revisions to the lambda cold dark matter model, and perhaps even provide clues to unknown aspects of physics. But if it turns out to be an illusion, an artifact of our limited observational techniques, then it will serve as a reminder that the universe is still full of surprises, and that our quest to understand it is far from over. Either way, the search for answers will push the boundaries of our knowledge, leading us deeper into the mysteries of the cosmos. If the Hercules-Corona Borealis Great Wall is truly as large as the data suggests, then it forces us to rethink the limits of structure formation in the universe. The current models of cosmology, based on the principles of gravity, dark matter, and the expansion of space, struggle to explain how such an immense structure could have formed within the 13.8 billion year history of the universe. Even with the most optimistic estimates of how quickly matter can clump together under gravitational attraction, the existence of a structure spanning over 10 billion light-years seems impossible within the known age of the cosmos. One possible explanation is that this structure is much older than previously assumed. If the Hercules-Corona Borealis Great Wall is a relic from an earlier cosmic era, it could suggest that the early universe had different conditions than what our models currently predict. Perhaps there was a period of rapid structure formation that allowed vast cosmic walls to emerge before the effects of dark energy began accelerating the expansion of the universe. This would imply that our understanding of cosmic evolution is missing a crucial piece. Alternatively, this vast galactic wall could be an illusion caused by the large-scale distribution of voids, immense regions of empty space with very few galaxies. If these voids are arranged in a certain way, they could create the appearance of a massive coherent structure when in reality, the galaxies within the Great Wall might not be as gravitationally connected as they seem. However, this explanation still doesn't fully account for the unusual clustering of gamma-ray bursts that initially led to its discovery. If this structure is real, it also raises questions about the influence of dark matter. Dark matter is an invisible substance that interacts gravitationally but does not emit, absorb, or reflect light. It is thought to form the scaffolding upon which galaxies and galaxy clusters assemble. If dark matter plays a significant role in shaping the Hercules-Corona Borealis Great Wall, then this might indicate that dark matter is distributed in a way that contradicts our current understanding. Some researchers have speculated that dark matter may form large-scale filaments and walls that guide the formation of galaxies, and this structure could be an extreme example of that process. Beyond dark matter, there is also the mystery of dark energy, the force driving the accelerated expansion of the universe. If dark energy does not act uniformly across the cosmos, but instead fluctuates in strength over large distances, it could explain why structures like this are able to persist despite the expansion of space. Some alternative models of cosmology suggest that dark energy could be interacting with matter in ways that cause certain regions of the universe to expand at different rates. If this is true, then the Hercules-Corona Borealis Great Wall could be located in a part of the universe where dark energy's effects are weaker, allowing gravity to dominate and form massive structures. Another radical idea is that the Great Wall could be evidence of an entirely new force of nature. In addition to gravity, electromagnetism, and the nuclear forces, could there be a previously undiscovered fundamental interaction that influences the large-scale arrangement of matter in the universe? Some theoretical physicists have proposed modifications to Einstein's theory of general relativity that might allow for such a force to exist, but so far, no definitive evidence has been found. One particularly intriguing possibility is that this structure might not be a product of normal cosmic evolution at all, but rather a remnant of an ancient phase transition in the universe's history. Just as water can freeze into ice or boil into steam, the early universe may have undergone phase transitions that affected the distribution of matter. If an early cosmic phase transition created a preferred pattern for galaxy formation, then the Hercules-Corona Borealis Great Wall could be an imprint of that ancient process. This idea ties into a larger debate about the nature of the early universe. Some cosmologists have suggested that the universe may have gone through multiple epochs of expansion and contraction before settling into its current state. If true, then structures like this could be fossils from a previous era of the cosmos, revealing clues about conditions that existed long before the formation of galaxies as we know them. Additionally, there is speculation that this structure could be linked to anomalies in the cosmic microwave background, CMB, the afterglow of the Big Bang. The CMB is remarkably uniform, but subtle variations in temperature suggest that some regions of the early universe had slightly different densities. Some researchers have noticed unexplained patterns in the CMB that seem to align with the locations of large-scale cosmic structures. Could the Hercules-Corona Borealis Great Wall be part of a larger pattern that traces back to the beginning of time itself? If we take this idea a step further, we might even consider whether this structure is evidence of a cosmic scale pattern in the fabric of the universe. Some scientists have proposed that the universe might be structured in a way that resembles fractals, mathematical patterns that repeat at different scales. If this is the case, then the Hercules-Corona Borealis Great Wall could be just one layer of a much larger, hierarchical arrangement of matter, with even greater structures yet to be discovered. Another mind-bending possibility is that this structure could be a direct sign of the multiverse. Some theories suggest that our universe is just one of many, and that vast structures like this might be seams where different regions of space-time interact. If the Hercules-Corona Borealis Great Wall represents a boundary between different cosmic domains, it could provide indirect evidence that other universes exist beyond our own. Of course, all of these ideas remain speculative until more data is collected. The next step in solving this mystery is to conduct deeper surveys of the region using both optical and radio telescopes. Future missions, such as the Square Kilometre Array, SKA, and the James Webb Space Telescope, will allow astronomers to probe the distribution of galaxies in unprecedented detail, potentially revealing whether this structure is truly as vast as it appears. If further observations confirm the existence of the Hercules-Corona Borealis Great Wall, it will force us to rethink everything we know about the large-scale structure of the universe. It could indicate that our models of cosmic evolution need to be revised, or it could reveal entirely new physics that govern how matter is distributed across billions of light years. Regardless of the final outcome, the search for answers about this colossal structure represents the very essence of scientific discovery. Every time we uncover something unexpected in the cosmos, we are reminded of how much we still have to learn. The Hercules-Corona Borealis Great Wall stands as one of the greatest puzzles in modern astronomy, a challenge that could redefine our understanding of the universe in ways we can scarcely imagine. For now, it remains an enigma, a massive, seemingly impossible feature in the cosmic landscape that defies explanation. Whether it turns out to be a fundamental aspect of the universe's structure or a misinterpretation of observational data, its discovery has already expanded the boundaries of what we consider possible. If the Hercules-Corona Borealis Great Wall is truly a real, coherent structure, it means the universe may contain an underlying order that we do not yet fully comprehend. The scale of this structure is so immense that it raises profound questions about how matter is arranged on the largest scales. It also suggests that the current standard model of cosmology may be incomplete, missing key insights into how the early universe evolved. One of the biggest mysteries surrounding this galactic wall is how it managed to form despite the known limitations of cosmic structure growth. According to the lambda cold dark matter model, the universe should not have structures larger than about 1.2 billion light-years due to the constraints of cosmic inflation and the expansion of space. Yet, the Hercules-Corona Borealis Great Wall spans over 10 billion light-years, seemingly contradicting these predictions. One possible explanation is that this structure formed in a region of space where the density of dark matter was higher than usual, allowing gravity to pull galaxies together at an accelerated rate. dark matter is the invisible substance that makes up most of the universe's mass, and it serves as the cosmic framework upon which galaxies form. If this region contained an exceptionally high concentration of dark matter, then the process of galaxy clustering could have occurred more rapidly, leading to the formation of a structure much larger than expected. However, there are problems with this idea. The presence of dark matter alone does not explain why galaxies in this vast wall appear to be aligned in a coherent pattern. Normally, galaxy clusters form in a somewhat random distribution, following the large-scale filamentary structure of the cosmic web. The Hercules-Corona Borealis Great Wall, on the other hand, exhibits an unusually high degree of alignment, suggesting that an unknown force or process may have influenced its formation. Another potential explanation is that this structure is a relic of an ancient cosmic phase transition. In the early universe, the distribution of matter was not uniform. As the universe cooled, certain regions condensed into galaxies while others remained void-like. If there was a unique phase transition that influenced how matter clumped together, it could have led to the formation of massive structures like this. Some theorists propose that exotic physics in the early universe, such as interactions between dark energy and dark matter, may have created conditions that allowed such an enormous structure to emerge. This hypothesis is particularly intriguing because it suggests that the Hercules-Corona Borealis Great Wall is not just an anomaly but a key to unlocking new physics. If this structure represents a fundamental pattern in the universe, it could indicate that similar, even larger structures exist beyond our current observational limits. One of the most speculative yet fascinating possibilities is that this Great Wall is a remnant of an earlier cosmic epoch that predates the current expansion of the universe. Some theories suggest that the universe has gone through cycles of expansion and contraction, with each cycle leaving behind structural imprints. If this is the case, then the Hercules-Corona Borealis Great Wall could be a remnant from a previous cosmic phase, a fossilized structure that has persisted despite the ongoing expansion of space. Alternatively, the structure could be an illusion caused by a statistical clustering of galaxies. When astronomers analyze data from deep space surveys, they rely on sampling methods that can sometimes create the appearance of large-scale patterns where none actually exist. If future studies with more precise instruments reveal that the individual galaxy clusters within the wall are not as strongly connected as they appear, then the structure might turn out to be less extraordinary than it currently seems. However, if future observations confirm that this vast cosmic wall is real, it will challenge fundamental assumptions about the universe's structure. It could mean that the forces shaping the cosmos are more complex than we currently understand and that there are hidden interactions between dark matter, dark energy, and the fabric of space-time itself. There is also the possibility that the Hercules-Corona Borealis Great Wall is evidence of a larger, cosmic-scale pattern that we have yet to decipher. Some scientists have proposed that the universe exhibits fractal-like properties, with structures repeating at different scales. If this is true, then this Great Wall could be part of an even more massive cosmic framework, one that extends beyond the observable universe. In the coming decades, new telescopes and observational technologies will allow us to probe deeper into the cosmos and test these ideas. The Vera C. Rubin Observatory, set to become operational soon, will conduct extensive sky surveys that could reveal more details about the large-scale distribution of galaxies. Additionally, radio telescopes like the Square Kilometre Array, SK, will provide new insights into the structure of cosmic filaments and voids. If future studies confirm the existence of the Hercules-Corona Borealis Great Wall, it could redefine our understanding of the universe in ways we cannot yet imagine. It would suggest that the cosmos is structured in a way that challenges conventional physics, potentially leading to new discoveries about the nature of space-time, gravity, and the formation of large-scale cosmic structures. Regardless of the final answer, the very existence of this mystery reminds us of the vast unknowns that still exist in the universe. Every time we uncover something unexpected, we are faced with the realization that we are only beginning to scratch the surface of cosmic knowledge. The Hercules-Corona Borealis Great Wall stands as a testament to the grandeur and complexity of the cosmos, a puzzle that may take generations to fully unravel. If the Hercules-Corona Borealis Great Wall truly exists as a coherent, gravitationally bound structure, it forces us to question whether our current understanding of cosmic evolution is fundamentally incomplete. The implications are staggering. Does this mean the universe has larger structures than we ever anticipated? Could it mean our models of cosmic inflation, structure formation, and even dark energy need revision? The scientific community is divided, but one thing is clear: this discovery has set off a wave of inquiry that could redefine what we know about the cosmos. One of the biggest issues astronomers face in studying such a vast structure is that it exists at an immense distance from Earth. The light from these galaxies has traveled for billions of years to reach us, meaning that when we observe them, we are seeing them as they existed in the past. If the Hercules-Corona Borealis Great Wall is real, then it means this structure already existed when the universe was much younger. This raises another profound question: how could such a massive cosmic wall have formed so early? The standard model of cosmology suggests that large-scale structures formed gradually through the gravitational attraction of matter. Small density fluctuations in the early universe, detected in the cosmic microwave background, CMB, eventually grew into galaxies, clusters, and cosmic filaments. However, if a structure as vast as this already existed billions of years ago, it implies that something must have accelerated the formation of matter on an unprecedented scale. Could this mean that our estimates of cosmic inflation, the rapid expansion that occurred fractions of a second after the Big Bang, are incorrect? The inflationary model is widely accepted because it explains why the universe appears so uniform on large scales. However, some theorists argue that if inflation had different properties than currently assumed, it could have led to the formation of gigantic structures early in cosmic history. This would require rethinking the physics of the universe's first moments. Another possibility is that dark matter played a more dominant role in early structure formation than we currently believe. Dark matter is thought to act as a gravitational skeleton for galaxies and clusters, pulling ordinary matter together. If dark matter had an uneven distribution in the early universe, it could have caused some regions to develop enormous structures while others remained empty voids. However, this would require modifications to our current models of how dark matter interacts with itself and with normal matter. Some researchers have also proposed that the Hercules-Corona Borealis Great Wall might not be a single, gravitationally bound structure but rather a statistical alignment of galaxy clusters that only appears connected from our perspective. Large-scale sky surveys rely on statistical methods to identify patterns, and there is always a chance that what looks like a coherent structure is actually a collection of unrelated objects that just happen to be in a similar region of space. However, this explanation does not fully account for the observed clustering of gamma-ray bursts, which was the initial clue leading to this discovery. The presence of such an enormous structure also challenges the so-called cosmological principle, one of the fundamental assumptions of modern astrophysics. This principle states that, on large enough scales, the universe should appear roughly the same in all directions, homogeneous and isotropic. The discovery of structures as vast as the Hercules-Corona Borealis Great Wall suggests that the universe might not be as uniform as we thought. If confirmed, this could have profound implications for how we understand cosmic evolution. Some physicists have even speculated that this structure could be a remnant of a previous phase in the universe's history, possibly from a time before the Big Bang as we understand it. Certain cosmological theories propose that the universe undergoes cycles of expansion and contraction, sometimes called the Big Bounce model. If true, structures like this could be leftover imprints from a previous universe that existed before our own. While this idea is still highly speculative, it highlights the level of uncertainty we face when studying cosmic structures on this scale. There is also the possibility that the Hercules-Corona Borealis Great Wall is not simply a natural cosmic formation but rather evidence of unknown physics at work. Could there be forces beyond gravity shaping the distribution of galaxies? Some alternative theories of gravity, such as modified Newtonian dynamics, MOND, or emergent gravity, suggest that our understanding of how mass behaves on the largest scales might be flawed. If these theories are correct, then structures like this could be revealing hidden aspects of fundamental physics. In the coming years, more advanced observational tools will help refine our understanding of this cosmic anomaly. The James Webb Space Telescope, with its ability to peer deep into the early universe, could provide more insight into the distribution of galaxies within the Great Wall. Additionally, next-generation radio telescopes, like the Square Kilometer Array (SKA), could map the distribution of hydrogen gas across cosmic filaments, helping to determine whether the structure is truly gravitationally bound or just an observational illusion. If the Hercules-Corona Borealis Great Wall is confirmed as a real, physically connected structure, it will stand as one of the greatest challenges to modern cosmology. It would suggest that there are forces, interactions, or early universe conditions that we do not yet understand. Whether this leads to new physics, modifications of the Standard Model, or an entirely new paradigm for cosmology remains to be seen. But beyond the scientific implications, this discovery reminds us of the sheer scale and mystery of the universe. The cosmos is vast beyond comprehension, filled with structures so large they defy human intuition. Even after centuries of studying the stars, we are still uncovering surprises that force us to question what we thought we knew. Perhaps the most exciting aspect of the Hercules-Corona Borealis Great Wall is that it represents the unknown. It is a reminder that the universe still holds secrets waiting to be uncovered, mysteries that challenge our greatest theories, and discoveries that could redefine the way we see reality itself. And as long as there are mysteries like this, the pursuit of cosmic knowledge will never end. If the Hercules-Corona Borealis Great Wall is indeed real and not a statistical illusion, it may indicate that the universe's large-scale structure is far more complex than previously thought. Astronomers have long believed that the cosmic web, an intricate network of filaments, voids, and clusters, forms the backbone of the universe. However, this wall's sheer size calls into question the limits of that structure. One possibility is that the Hercules-Corona Borealis Great Wall represents an extreme case of galactic clustering, where multiple filaments of the cosmic web intersect and create an exceptionally dense region of matter. If so, it might suggest that the universe's structure is more hierarchical than we currently believe, with clusters forming superclusters, which in turn form even larger structures that extend beyond our current observational limits. But if this is true, why have we not detected similar structures elsewhere in the universe? The Sloan Great Wall and the CFA2 Great Wall are large, but they are nowhere near the scale of the Hercules-Corona Borealis Great Wall. Could this mean that the early universe had conditions that allowed such a massive formation in this particular region, but not elsewhere? If so, this could point to asymmetries in the distribution of matter in the early cosmos, an idea that contradicts the widely accepted principle that the universe should be uniform on large scales. There is also the question of how such a structure would impact the movement of galaxies within it. In a gravitationally bound system, galaxies exert a pull on one another, affecting their velocities. If the Hercules-Corona Borealis Great Wall is truly connected, then we would expect to see patterns in the way galaxies move within it. Future studies using redshift measurements and velocity mapping could help determine whether these galaxies share a common motion, which would provide stronger evidence that they are part of a single, coherent structure rather than a chance alignment. Another way to verify the reality of this galactic wall is to look at its gravitational effects on surrounding space. A structure of this size should have a measurable influence on cosmic expansion in its vicinity. If it is real, we might expect to see distortions in the cosmic microwave background radiation or deviations in the flow of nearby galaxies. If these effects are found, it would provide additional confirmation that the structure is not merely a statistical illusion, but a genuine feature of the universe. One of the more radical ideas proposed to explain such a massive structure is the possibility of a yet undiscovered force influencing the large-scale arrangement of matter. Some physicists speculate that the universe could contain unknown fields or forces that only become relevant at cosmological scales. If such a force exists, it might explain why structures like this appear to defy current gravitational models. Another theory suggests that interactions between dark matter and dark energy may be more complex than we currently assume. Dark energy is the mysterious force driving the accelerated expansion of the universe, but its nature remains largely unknown. If dark energy has regional variations, it could have influenced the early formation of structures like the Hercules-Corona Borealis Great Wall. This idea is speculative, but it highlights the potential for new physics hidden within the universe's largest structures. Some theorists have even suggested that the Hercules-Corona Borealis Great Wall could be evidence of a multiverse, a collision between our universe and another in the distant past. Certain cosmological models predict that if our universe exists within a larger multiverse, interactions between different bubble universes could leave imprints on the cosmic structure. If this wall represents such an imprint, it could be one of the first observable clues pointing toward the existence of other universes beyond our own. While these ideas remain purely hypothetical for now, they underscore how little we truly understand about the cosmos. The mere possibility of a structure this vast forces us to rethink fundamental assumptions about the universe's evolution, its composition, and even the laws that govern it. As telescopes become more powerful, astronomers will continue to probe deeper into space, searching for more evidence that could confirm or refute the existence of this Great Wall. Future missions, such as the Nancy Grace Roman Space Telescope, will provide high-resolution data on the large-scale distribution of galaxies, allowing scientists to refine their models and test new hypotheses. Regardless of what future observations reveal, the discovery of the Hercules-Corona Borealis Great Wall has already changed the way we think about the universe. If confirmed, it would be the largest known structure in existence, a cosmic enigma that stretches across billions of light-years, challenging the very foundations of astrophysics. If it turns out to be an illusion, it still serves as a reminder that our understanding of the cosmos is constantly evolving, and that every new discovery, whether real or apparent, brings us closer to unraveling the ultimate mysteries of the universe. But perhaps the most profound aspect of this discovery is what it represents: the unknown. The vastness of space is filled with unanswered questions, and every time we look deeper, we find something that forces us to rethink our place in the cosmos. The Hercules-Corona Borealis Great Wall is more than just a collection of galaxies. It is a challenge, a puzzle, and a testament to the boundless mysteries of the universe. And as long as we continue to explore, we will never run out of wonders to uncover. The true scale of the Hercules-Corona Borealis Great Wall is so vast that even attempting to grasp its enormity can feel overwhelming. When we speak of distances measured in billions of light-years, we are discussing dimensions that exceed human comprehension. This structure is not just larger than galaxies or galaxy clusters, it is larger than any known cosmic formation, spanning a region of space so immense that even light, traveling at 300,000 kilometers per second, would take billions of years to cross it. To put this into perspective, consider that our Milky Way galaxy is about 100,000 light-years across. The observable universe itself stretches roughly 93 billion light-years in diameter. Yet this single galactic structure spans over 10 billion light-years. This means that if it were somehow visible from Earth, it would cover a substantial fraction of the entire sky. It is so large that, even at the speed of light, signals sent from one end of the structure to the other would take eons to reach their destination. But the enormity of the Hercules-Corona Borealis Great Wall is not just a question of scale, it is a direct challenge to everything we thought we knew about cosmic structure formation. The standard model of cosmology tells us that gravity is the dominant force responsible for shaping the universe's large-scale structure. Small variations in the density of matter in the early universe gradually grew under gravity's pull, forming stars, galaxies, and clusters over billions of years. However, structures this massive should not have had enough time to form, even over the universe's 13.8 billion year history. This raises several possibilities. One is that our timeline for cosmic structure formation is incorrect. If the Hercules-Corona Borealis Great Wall is real, then the processes that shaped the universe must have acted far more efficiently than previously believed. Perhaps there were early fluctuations in matter density that were significantly stronger than those detected in the cosmic microwave background. If true, it could suggest that the universe's initial conditions were far more uneven than expected, leading to extreme cases of galactic clustering. Another possibility is that there were unknown forces at work during the universe's infancy. Could there be aspects of gravity that we have yet to understand? Some physicists propose that gravity itself might behave differently on cosmological scales, meaning that our equations, based on Einstein's general relativity, may not fully capture the way mass interacts at the largest scales. If gravity was stronger or more dynamic in the early universe, it could explain how such an enormous wall of galaxies managed to form. Alternatively, the existence of this massive structure might suggest that dark matter and dark energy played a much larger role in shaping the cosmic web than previously thought. Dark matter is theorized to account for nearly 85% of the total mass in the universe, yet it remains invisible and interacts only through gravity. If dark matter was distributed in a way that we do not yet understand, it could have caused the rapid formation of large-scale structures like the Hercules-Corona Borealis Great Wall. Dark energy adds another layer of complexity. Currently, it is believed to be responsible for the accelerated expansion of the universe. If dark energy varied across different regions of space, it might have influenced how galaxies clustered, allowing for the formation of ultra-massive structures in some areas while preventing them in others. If this were true, it could mean that the cosmic expansion we observe today is not as uniform as we once assumed. One of the most intriguing possibilities is that the Hercules-Corona Borealis Great Wall is evidence of a hidden connection between cosmic structure and fundamental physics. Some theories propose that the early universe underwent phase transitions, similar to how water freezes into ice. These transitions might have created regions of high and low density, leading to the formation of massive structures in some areas while leaving vast cosmic voids in others. If true, it could indicate that the formation of the universe was not entirely random, but was instead governed by deeper physical laws that we have yet to uncover. There is also the controversial idea that this structure could be a remnant of an even larger cosmic event, perhaps an imprint from a past universe or a collision between different regions of space-time. Some cosmological theories suggest that the universe might be part of a multiverse, with different universes interacting in ways that leave behind observable effects. If the Hercules-Corona Borealis Great Wall is a result of such an interaction, it could be the first tangible evidence that our universe is not alone. Despite these possibilities, some scientists remain skeptical of the wall's existence. The data that led to its discovery is based primarily on the distribution of gamma-ray bursts, which are some of the most energetic events in the universe. These bursts are often associated with the deaths of massive stars, and their distribution can be used to map the locations of galaxies. However, gamma-ray bursts are rare, and their locations might not always accurately represent the true large-scale structure of the universe. To confirm the Hercules-Corona Borealis Great Wall, astronomers will need to gather additional data using different observational methods. Large-scale galaxy surveys, such as those conducted by the Sloan Digital Sky Survey, can provide a more detailed map of how galaxies are distributed in the region. Future telescopes, like the Vera C. Rubin Observatory, will allow scientists to detect fainter and more distant galaxies, helping to determine whether they align with the pattern suggested by the gamma-ray bursts. Another approach is to study the cosmic microwave background radiation, the afterglow of the Big Bang. If a structure this large exists, it should leave a detectable imprint on the CMB, subtly altering the temperature fluctuations observed across the sky. If such an imprint is found, it would provide strong evidence that the wall is a genuine feature of the universe, and not just a statistical anomaly. Even if the Hercules-Corona Borealis Great Wall is ultimately proven to be an illusion, the mere possibility of its existence has already pushed the boundaries of astrophysics. It has forced scientists to question the limits of the universe's largest structures and consider the possibility that our understanding of cosmic evolution is incomplete. Whether real or not, this discovery is a reminder that the universe is still full of surprises. The search for answers will continue, and as our telescopes and technology improve, we may uncover even larger and more mysterious structures lurking in the depths of space. The Hercules-Corona Borealis Great Wall is a testament to the scale of the cosmos, a reminder that no matter how much we learn, the universe will always remain beyond our full comprehension. And yet, it is precisely this mystery that drives us to explore further, to question deeper, and to seek out the unknown. The cosmos is a vast, uncharted frontier, filled with wonders yet to be discovered. Whether the Hercules-Corona Borealis Great Wall is the largest structure in the universe or merely a stepping stone to even greater revelations, it has already changed the way we view our place in the grand expanse of space. The implications of the Hercules-Corona Borealis Great Wall extend far beyond just its size. If it is real, it would force us to reconsider the fundamental principles of cosmology, potentially leading to groundbreaking discoveries about the structure of the universe itself. One of the most profound consequences would be its impact on the cosmological principle, the assumption that, on large scales, the universe is homogeneous and isotropic. This principle has been a cornerstone of modern astrophysics, forming the foundation of our understanding of the universe's expansion, cosmic evolution, and even the equations that govern general relativity. But if the Hercules-Corona Borealis Great Wall exists, it directly contradicts this principle. A structure of such massive scale implies that the universe is not as uniform as we once believed. This could mean that our cosmic models, which rely on the assumption that matter is evenly distributed across the universe at large scales, may need to be revised. It could also suggest that the way galaxies cluster is not entirely random, but instead follows underlying patterns that we have yet to fully understand. One potential explanation for this extreme clustering is that regions of the universe may have formed under different conditions due to quantum fluctuations in the early universe. During the period of cosmic inflation, an extremely brief and rapid expansion of the universe that occurred just after the Big Bang, tiny quantum variations in energy density could have been stretched across vast cosmic scales. These variations could have later influenced the formation of galaxies, causing certain regions to become extraordinarily dense while others remained relatively empty. If the Hercules-Corona Borealis Great Wall is a product of such an effect, it could provide new insights into the physics of the very early universe. It might even offer clues about what existed before the Big Bang. Some cosmological models suggest that our universe emerged from a previous state of existence, possibly as part of a cyclic or multiverse model. If structures like this Great Wall are relics of earlier cosmic phases, they could serve as fossilized imprints of events that occurred before our observable universe even began. Another idea worth exploring is the possibility that our understanding of dark matter and dark energy is incomplete. These two mysterious components make up roughly 95% of the universe's total mass energy content, yet they remain poorly understood. Dark matter is believed to provide the gravitational scaffolding that allows galaxies and galaxy clusters to form, while dark energy is responsible for the accelerated expansion of the universe. If these forces interact in ways we do not yet comprehend, they might be responsible for shaping massive structures like the Hercules-Corona Borealis Great Wall. For example, some theories propose that dark matter could be self-interacting, meaning that it doesn't just passively clump under gravity but also experiences additional forces that affect its distribution. If dark matter behaves differently on cosmological scales than it does on galactic scales, this could explain why certain regions of the universe, like the area containing the Great Wall, appear to have formed extreme structures that defy expectations. Similarly, dark energy might not be a uniform force but rather something that varies across space and time. Some cosmologists have suggested that dark energy could be influenced by the large-scale distribution of matter, meaning that in certain regions, its effects might be different from the standard model. If dark energy has local fluctuations, it might have contributed to the formation of an enormous structure like the Hercules-Corona Borealis Great Wall, allowing it to exist despite the constraints of our current models. There is also the possibility that we are observing the effects of a previously unknown force or fundamental interaction at work in the universe. Some physicists have proposed modifications to general relativity, suggesting that gravity might behave differently on the largest cosmic scales. If this is true, then the formation of the Hercules-Corona Borealis Great Wall might be an indication that our current understanding of gravity needs to be expanded. One particularly intriguing idea is that this massive structure could be evidence of a connection between our universe and another. Some models of cosmology propose that the universe exists within a larger multiverse, where different regions of space-time could have distinct physical laws. If another universe had an influence on our own in the distant past, perhaps through a collision between cosmic domains, this could have left behind large-scale anomalies like the Hercules-Corona Borealis Great Wall. There is also the question of whether this structure is truly gravitationally bound or simply an illusion created by the way we observe distant galaxies. Some astronomers suggest that the clustering of gamma-ray bursts used to detect this structure might not actually correspond to a continuous, physical object but rather to a statistical pattern that only appears significant due to the limitations of our data. Future observations using more precise measurements of galaxy motion and large-scale structure mapping will be needed to confirm whether the Hercules-Corona Borealis Great Wall is a true physical entity, or merely a mirage in the cosmic landscape. Regardless of whether the structure turns out to be real or an observational artifact, its discovery has already had a profound impact on astronomy. It has forced scientists to ask new questions about the nature of cosmic structure, the limits of the observable universe, and the underlying laws that govern reality itself. Even if the Hercules-Corona Borealis Great Wall is ultimately proven to be an illusion, the process of investigating it will undoubtedly lead to new discoveries and a deeper understanding of the cosmos. Looking ahead, new technologies and upcoming astronomical surveys will allow us to probe even deeper into space and gather more precise data on the distribution of galaxies. The next generation of telescopes, such as the James Webb Space Telescope, the Nancy Grace Roman Space Telescope, and the Vera C. Rubin Observatory, will provide unprecedented insights into the large-scale structure of the universe. These instruments will allow us to map the cosmos in greater detail, potentially revealing even more enormous structures hidden beyond our current observational limits. If more structures like the Hercules-Corona Borealis Great Wall are found, it could signal a paradigm shift in our understanding of the universe. Instead of viewing the cosmic web as a relatively uniform and evenly distributed network, we might have to consider the possibility that the universe is composed of an intricate and highly structured hierarchy of matter, with massive walls and filaments stretching across billions of light years. This raises another profound question. If structures larger than the Hercules-Corona Borealis Great Wall exist, could there be a limit to how big the universe's structures can get? Is there a fundamental boundary to the size of cosmic formations, or could we continue to find even greater walls, voids, and clusters as our observational capabilities improve? One speculative yet fascinating idea is that the universe itself might have a fractal-like structure, where patterns repeat on ever larger scales. If this is true, then the structures we observe today might just be part of an even grander cosmic architecture, one that extends beyond our current observational reach and perhaps even beyond our ability to comprehend. No matter what the future holds, the study of the Hercules-Corona Borealis Great Wall is a testament to humanity's relentless curiosity. It reminds us that the universe is far more complex and mysterious than we can currently explain, and that each discovery leads to new questions rather than final answers. The cosmos is a vast, ever-expanding frontier, and as long as we continue to explore it, we will never run out of mysteries to uncover. The possibility that the universe follows a fractal-like structure is a compelling one. Fractals are mathematical patterns that repeat at different scales, and some scientists have proposed that the large-scale distribution of galaxies might exhibit a similar property. If this idea holds true, then structures like the Hercules-Corona Borealis Great Wall might not be outliers, but rather part of a repeating pattern of cosmic formation stretching across the universe. However, there is an inherent problem with this notion. The standard model of cosmology suggests that at sufficiently large scales, the universe should become homogeneous, meaning that no particular region should be significantly more dense or structured than any other. But the discovery of immense structures like the Great Wall challenges this assumption, suggesting that there may be patterns in the universe's organization that we have yet to fully understand. If more structures of similar or even larger sizes are found, it could mean that the distribution of matter in the universe is governed by unknown physical laws that allow for the formation of these colossal cosmic features. This leads to another fascinating question: could there be a fundamental limit to the size of cosmic structures? The observable universe is estimated to be about 93 billion light-years in diameter, but the true size of the entire universe could be vastly larger, or even infinite. If the universe has a finite size, then there must be an upper limit to how large structures can get, simply because there is only so much space available. But if the universe is infinite, then in theory, there could be even larger walls and clusters of galaxies stretching beyond our current observational limits. One way to explore this question is to analyze the cosmic web, the vast, interconnected network of galaxies and dark matter that spans the universe. This web-like structure is thought to have formed due to the influence of dark matter, which acts as an invisible scaffolding that guides the motion of galaxies. If the Hercules-Corona Borealis Great Wall represents one of the largest known filaments of this web, then studying it could provide crucial insights into how cosmic structures evolve over time. Some researchers have suggested that the formation of such large structures might be connected to the initial conditions of the universe itself. During the first few moments after the Big Bang, tiny fluctuations in energy density would have determined the distribution of matter as the universe expanded. If these fluctuations were more extreme than previously thought, they could have led to the creation of enormous cosmic structures like the Great Wall. This could mean that our understanding of the early universe is incomplete, and that there may have been factors influencing cosmic evolution that we have yet to identify. Another possibility is that the structure is a remnant of a previous phase of the universe's existence. Some cosmological theories propose that our universe has gone through cycles of expansion and contraction, with each cycle leaving behind imprints on the large-scale structure of space. If this is the case, then the Hercules-Corona Borealis Great Wall might be a relic of a much earlier cosmic epoch, providing a glimpse into the history of the cosmos before the Big Bang as we understand it. If we accept that structures like this exist, then we must also reconsider how gravity functions on the largest cosmic scales. According to Einstein's theory of general relativity, gravity should act uniformly across space, causing galaxies to cluster in a predictable manner. But if structures of this magnitude exist, it may indicate that gravity behaves differently on vast scales than we currently assume. Some alternative theories of gravity, such as modifications to general relativity or the inclusion of additional dimensions beyond the three we experience, might be necessary to explain such anomalies. There is also the question of dark energy, the mysterious force that is causing the accelerated expansion of the universe. If dark energy varies across space, it could create regions where matter clumps together in unexpected ways, forming structures like the Hercules-Corona Borealis Great Wall. Some researchers have proposed that dark energy could be influenced by the distribution of galaxies, meaning that the universe's expansion might not be as uniform as we once believed. One of the most radical hypotheses is that structures like this could be evidence of interactions between our universe and other universes. Some versions of the multiverse theory suggest that different universes could occasionally interact, leaving behind large-scale imprints in the cosmic structure. If another universe had a gravitational influence on our own at some point in the past, it might have contributed to the formation of such an enormous structure. Observationally, the biggest challenge is confirming whether the Hercules-Corona Borealis Great Wall is truly a single, continuous structure or merely an illusion created by the way we measure gamma-ray bursts. The current data relies on the assumption that these bursts trace the distribution of galaxies, but future surveys using more direct measurements of galaxy clustering and large-scale cosmic mapping will be needed to verify its existence. Upcoming projects like the Euclid Space Telescope and the Square Kilometre Array (SK) will allow astronomers to study the universe's large-scale structure with unprecedented precision. These instruments will help determine whether structures like the Hercules-Corona Borealis Great Wall are outliers or if they represent a fundamental aspect of cosmic organization. If more such structures are found, it could lead to a major revision of our cosmological models, potentially introducing new physics that go beyond the current standard model. The implications of such a discovery would be profound, possibly changing our understanding of the universe's origins, evolution, and ultimate fate. Ultimately, the Hercules-Corona Borealis Great Wall is more than just an enormous structure. It is a cosmic mystery that challenges our most fundamental assumptions about the universe. Whether it turns out to be a true physical feature or an observational artifact, its discovery has already had a lasting impact on astrophysics. It forces us to question the very nature of the cosmos, and encourages us to keep searching for answers to the biggest questions in science. As technology advances and our ability to observe the universe improves, we may one day unlock the secrets of this massive structure. But until then, it remains one of the greatest unsolved mysteries of the cosmos, a testament to the vast, complex, and still largely unexplored nature of our universe. The Hercules-Corona Borealis Great Wall is not just an isolated mystery, but a part of a broader challenge in understanding how the universe is structured. It raises profound questions about the formation of the cosmos, the limits of known physics, and whether our models of the universe are complete. While it is often categorized as a supercluster complex, its sheer size and mass distribution defy conventional explanations. Some astronomers even question whether such vast structures can exist under the current lambda cold dark matter model, which is the leading framework explaining cosmic evolution. One of the most puzzling aspects of this massive structure is how it could have formed within the time frame of the universe's existence. Based on our understanding of cosmic inflation, the rapid expansion that followed the Big Bang, matter in the universe should be distributed in a relatively uniform way at large scales. While local variations exist due to gravitational attraction, the Hercules-Corona Borealis Great Wall appears to have a level of organization that suggests something more complex at play. If such an immense structure formed naturally, it implies that the universe's large-scale architecture is far more intricate than previously thought. One possibility is that cosmic filaments, huge, thread-like formations of dark matter and galaxies that connect clusters, played a key role in the development of this structure. These filaments create a cosmic web, where galaxies and clusters align along invisible strands of dark matter. However, the Hercules-Corona Borealis Great Wall is far more massive than typical filaments, leading some scientists to speculate that it could be the result of an extreme alignment of multiple filaments rather than a single, cohesive structure. Another potential explanation lies in the distribution of dark matter, the unseen substance that makes up roughly 85% of the universe's total mass. Dark matter interacts with regular matter through gravity but does not emit light, making it nearly impossible to detect directly. If the Hercules-Corona Borealis Great Wall is embedded in a vast, dense region of dark matter, it could have facilitated the gravitational clustering of galaxies on an unprecedented scale. If dark matter is the key to forming such enormous cosmic structures, it raises questions about the fundamental nature of this mysterious substance. Current theories suggest that dark matter consists of weakly interacting massive particles, WIMPs, but no direct evidence has confirmed their existence. Some alternative theories propose that dark matter could be an effect of modified gravity rather than a separate form of matter. If the Hercules-Corona Borealis Great Wall turns out to be a true anomaly, it may push scientists to reconsider the properties of dark matter or even propose new physics beyond our current understanding. Additionally, the structure may provide clues about the influence of dark energy, the force responsible for the accelerated expansion of the universe. If dark energy varies across different regions of space, it could explain why certain areas experience more clustering of matter than others. Some researchers have suggested that dark energy may interact with dark matter in ways we do not yet understand, potentially influencing the formation of supermassive cosmic structures. There is also the intriguing possibility that structures like the Hercules-Corona Borealis Great Wall are remnants of earlier cosmic epochs. Some cosmological models propose that the universe undergoes cycles of expansion and contraction, meaning that the observable universe we see today could be influenced by imprints from previous cycles. If this theory holds true, the Great Wall might be an ancient structure that predates the Big Bang as we currently understand it. One of the most extreme hypotheses is that the existence of such a large structure could hint at interactions between different universes. Some versions of the multiverse theory suggest that our universe may occasionally experience gravitational influences from neighboring universes, causing localized distortions in the large-scale structure of space. If another universe exerted a force on our own in the distant past, it might have contributed to the formation of the Hercules-Corona Borealis Great Wall. Regardless of the true nature of this cosmic enigma, one thing is certain: the Hercules-Corona Borealis Great Wall challenges many of our assumptions about the universe. Its discovery has sparked debates among astronomers and physicists, leading to new research aimed at refining our understanding of cosmic structure formation. Future observations will be crucial in determining whether this massive formation is truly a single, coherent structure, or merely an illusion caused by the way gamma ray bursts are distributed. Upcoming telescopes such as the Vera C. Rubin Observatory and the James Webb Space Telescope will provide new insights into galaxy distribution, potentially confirming or refuting the existence of other superstructures like this one. If more structures of similar magnitude are discovered, it could signal a paradigm shift in our understanding of cosmology. The standard model of the universe may need to be modified or expanded to account for these unexpected features. Alternatively, the discovery of new cosmic structures could validate existing theories while providing additional details about the way the universe evolved over billions of years. Ultimately, the Hercules-Corona Borealis Great Wall remains one of the most significant and perplexing discoveries in modern astronomy. It represents a frontier in our quest to understand the cosmos, reminding us that despite our technological advancements, the universe still holds mysteries that challenge our most fundamental scientific principles. As our observational capabilities improve, we may one day unlock the secrets of this colossal structure. But for now, it stands as a cosmic enigma, one that forces us to reconsider the very fabric of space and time. The search for answers continues, and with each new discovery, we move closer to unraveling the profound mysteries of the universe. The implications of the Hercules-Corona Borealis Great Wall's existence stretch far beyond just the structure itself. It forces us to question whether our current cosmological models are incomplete, and whether unknown forces or mechanisms are at play in shaping the universe. If such an enormous formation can exist, then what other colossal structures remain undiscovered? Could there be even larger formations lurking in the depths of the cosmos, hidden beyond the limits of our observational reach? One of the biggest challenges in studying the Great Wall is the nature of its detection. Unlike other massive cosmic structures, which are typically observed through direct surveys of galaxies, this structure was identified using gamma ray bursts, GRBs. These bursts are some of the most energetic events in the universe, resulting from the explosive deaths of massive stars or the collisions of neutron stars. Because GRBs are distributed across vast cosmic distances, they serve as useful markers for tracing large-scale structures. However, some scientists argue that using GRBs as a proxy for galaxy distribution may introduce biases, making it difficult to confirm whether the Hercules-Corona Borealis Great Wall is truly a single, coherent structure or an illusion created by sampling limitations. To address this uncertainty, astronomers are working on future surveys that will map the large-scale structure of the universe with much greater precision. The European Space Agency's Euclid mission, for example, will create a detailed 3D map of the cosmos, helping to refine our understanding of galaxy clustering and cosmic filaments. Meanwhile, the Square Kilometre Array, SKA, the world's largest radio telescope, will provide unprecedented insights into the distribution of galaxies and the role of dark matter in shaping cosmic structures. If these surveys confirm the existence of the Great Wall, it could lead to a fundamental shift in our understanding of cosmic evolution. One of the most perplexing aspects of the Great Wall is the question of how such a structure could have formed in the first place. According to current models, gravity alone should not have been able to assemble a structure of this magnitude within the lifetime of the universe. This suggests that either our understanding of cosmic structure formation is incomplete, or that unknown physical processes may be at work. Some scientists have proposed that exotic forms of dark matter, such as self-interacting dark matter or axions, could play a role in forming such large structures. Others suggest that modifications to Einstein's theory of general relativity might be necessary to explain the existence of the Great Wall. There is also the possibility that this massive structure is a result of anisotropies in the early universe, regions where matter was distributed unevenly due to quantum fluctuations during the inflationary epoch. If these fluctuations were more extreme than previously thought, they could have seeded the formation of structures far larger than expected. This could mean that the fundamental physics governing the early universe may be different from what our current theories predict. Another controversial idea is that the existence of the Hercules-Corona Borealis Great Wall could be evidence of cosmic strings, hypothetical one-dimensional defects in space-time that may have formed in the early universe. These cosmic strings, if they exist, could act as gravitational attractors, pulling vast amounts of matter into elongated structures. If such strings are real, they would not only explain the formation of the Great Wall but also provide a direct link between modern astrophysics and theories of high-energy particle physics. The discovery of structures like the Great Wall also raises questions about the ultimate fate of the universe. If matter continues to cluster into increasingly larger structures, will the universe eventually become dominated by vast superstructures? Or will dark energy's accelerating expansion tear these structures apart over time? Some theories suggest that as the universe expands, large-scale structures will eventually be stretched to the point where galaxies become isolated from one another, leading to a Big Freeze scenario where all cosmic activity gradually ceases. Others propose that the formation of such massive structures could trigger new gravitational effects, potentially influencing the long-term evolution of the cosmos in unexpected ways. The implications of these questions extend beyond astrophysics and into the realm of philosophy and existential inquiry. If our universe is structured in ways we do not yet understand, then what does that say about our place in the cosmos? Are we merely observers of a vast, chaotic universe, or is there an underlying order that we have yet to uncover? Could structures like the Hercules-Corona Borealis Great Wall be part of a grander cosmic design, one that hints at fundamental principles we have yet to grasp? One of the most tantalizing possibilities is that structures like this could be evidence of higher dimensional influences on our universe. Some theories in string theory and brane cosmology suggest that our universe may be embedded within a higher dimensional space. If these extra dimensions exert gravitational effects on our cosmos, they could create patterns and structures far beyond what conventional physics would predict. If this is the case, then the Hercules-Corona Borealis Great Wall could be an indirect sign of a deeper, more complex reality that lies beyond our perception. Regardless of the ultimate explanation, the discovery of such a massive structure is a humbling reminder of how little we truly know about the universe. Every time we think we have a solid understanding of the cosmos, new discoveries emerge that challenge our assumptions and push the boundaries of human knowledge. The Hercules-Corona Borealis Great Wall is one such discovery, a mystery that forces us to rethink our understanding of space, time, and the fundamental forces that govern reality. As we continue to explore the depths of the universe, one thing remains certain: the cosmos is far more complex, vast, and mysterious than we ever imagined. The search for answers is ongoing, and as new technologies and scientific advancements allow us to peer deeper into space, we may one day unlock the secrets of the largest structures ever discovered. Until then, the Hercules-Corona Borealis Great Wall stands as one of the greatest cosmic enigmas, a monument to the grandeur and mystery of the universe. The Hercules-Corona Borealis Great Wall remains one of the most profound challenges to our understanding of the universe, not just in its scale but in the questions it raises about the nature of cosmic evolution. If structures of this magnitude exist, then they may suggest that our current models of the universe are incomplete, requiring either revisions to established theories or the introduction of entirely new physics. The scientific community remains divided on how to interpret this massive formation, but regardless of the final answer, its discovery is a significant milestone in our quest to understand the cosmos. One of the most striking aspects of this superstructure is its relationship to the so-called cosmological principle. This principle, which underpins much of modern cosmology, states that on sufficiently large scales, the universe should appear homogeneous and isotropic, meaning it should look the same in all directions, with matter distributed fairly evenly. However, the existence of the Hercules-Corona Borealis Great Wall seems to violate this principle, suggesting that the universe may be more structured than we previously thought. If true, this could have profound implications for the standard model of cosmology and the fundamental assumptions guiding our understanding of the universe. The size of the Great Wall also raises questions about the timeline of cosmic structure formation. According to current models, the universe is approximately 13.8 billion years old, and structures have gradually formed through the influence of gravity, starting from small density fluctuations in the early universe. However, for a structure as massive as the Hercules-Corona Borealis Great Wall to form within this timeframe, it would require an enormous concentration of matter and an extraordinarily efficient process of galaxy clustering. This suggests that either our estimates of cosmic structure formation are incorrect or that unknown forces influence the development of such superstructures. Another possibility is that the Great Wall is not a singular, coherent structure but rather a series of interconnected galaxy clusters that only appear as a single entity from our perspective. If this were the case, it could mean that our observations are being affected by the limitations of our current measurement techniques, and what we see may be an illusion created by our methods of detecting gamma-ray bursts. Future studies will be necessary to confirm whether the Hercules-Corona Borealis Great Wall is a genuine, gravitationally bound structure or an artifact of observational biases. One avenue of exploration involves using alternative methods to map the distribution of galaxies within this region. While gamma-ray bursts provided the initial clue to its existence, astronomers are now turning to large-scale galaxy surveys, radio telescopes, and infrared observations to build a more comprehensive picture. The upcoming Nancy Grace Roman Space Telescope, for example, will allow for unprecedented wide-field observations that may help clarify the true nature of the Great Wall. If the structure is confirmed as a legitimate galactic formation, then it could force a re-evaluation of dark matter's role in shaping the universe. As previously mentioned, dark matter is an unseen substance that interacts with regular matter through gravity but does not emit or absorb light. It is thought to play a crucial role in the formation of galaxies and galaxy clusters, acting as a cosmic scaffolding that guides their development. However, if the Hercules-Corona Borealis Great Wall is as massive as it appears, it could mean that dark matter behaves in ways we do not yet understand. Some theories propose that dark matter may have different properties in different regions of the universe. If true, this could explain why certain areas contain such massive, interconnected structures while others remain relatively empty. Alternatively, it could suggest that dark matter interacts with itself in complex ways, forming structures far larger than previously predicted. If these ideas are correct, they would mark a major shift in our understanding of the nature of dark matter and its influence on the cosmos. There is also the possibility that the Great Wall's formation was influenced by primordial black holes, hypothetical black holes that may have formed in the early universe. Unlike black holes that formed from collapsing stars, primordial black holes could have originated from high-density fluctuations during the first moments of cosmic inflation. If these black holes clustered together, they could have acted as gravitational attractors, pulling vast amounts of matter into the structure we see today. This idea connects to a broader question: could the existence of such enormous structures provide clues about the conditions of the early universe? If the Hercules-Corona Borealis Great Wall formed unusually early, it could mean that the universe's initial conditions were different from what we currently believe. This might suggest that cosmic inflation, the rapid expansion that occurred immediately after the Big Bang, was more complex than we currently assume. Some versions of inflation theory propose that different regions of the universe expanded at different rates, leading to variations in the density of matter that could explain the formation of such massive structures. One of the most extreme possibilities is that the Great Wall is evidence of interactions between parallel universes. Some interpretations of string theory and the multiverse hypothesis suggest that our universe may occasionally experience gravitational influences from neighboring universes. If another universe had a close encounter with our own in the distant past, it could have created density variations in the cosmic web, leading to the formation of superstructures like the Hercules-Corona Borealis Great Wall. While this idea remains speculative, it highlights how discoveries like this push the boundaries of our knowledge. As our telescopes become more powerful and our computational models more advanced, we may find new ways to test these hypotheses and determine whether structures like this one can be explained by known physics or require entirely new frameworks. Another important question is whether structures like the Great Wall are common in the universe or if this is an isolated case. If astronomers discover more superstructures of similar scale, it could indicate that such formations are a natural feature of the cosmos rather than a rare anomaly. This would further challenge the cosmological principle and might require a revision of how we define large-scale structure in the universe. Conversely, if no other structures of this magnitude are found, it could mean that the Hercules-Corona Borealis Great Wall is a unique event, possibly the result of highly unusual conditions that existed in one particular region of the cosmos. This could provide valuable insights into the differences between various cosmic environments, and help us understand why some areas of the universe contain vast interconnected structures while others appear relatively empty. As technology advances, new observational tools may help us unlock more secrets about the Hercules-Corona Borealis Great Wall. The next generation of telescopes, including the Extremely Large Telescope, ELT, and the 30-meter telescope, TMT, will be capable of resolving distant galaxies with unprecedented detail. These instruments may allow scientists to map the precise distribution of matter within the Great Wall, confirming whether it is truly a singular structure or an illusion created by our current observational limitations. Regardless of what future research reveals, the Hercules-Corona Borealis Great Wall stands as a testament to the vastness and complexity of the universe. It is a reminder that, despite centuries of scientific progress, we are still in the early stages of understanding the full scale of cosmic structures. As new discoveries continue to reshape our understanding of the universe, this colossal formation will remain one of the greatest mysteries of modern astronomy, an enigma that challenges our very perception of reality. The search for answers continues, and with every new observation, we take another step toward unraveling the mysteries of the cosmos. Whether the Hercules-Corona Borealis Great Wall is a natural feature of the universe, a sign of unknown physics, or something even more profound, its existence is a reminder that the universe is far grander and more mysterious than we could have ever imagined. The mystery of the Hercules-Corona Borealis Great Wall extends beyond its sheer size. It forces us to question whether our understanding of cosmic evolution is fundamentally incomplete. This structure, spanning billions of light years, stands as a contradiction to the established notion that the universe should appear relatively uniform at sufficiently large scales. If such a behemoth can exist, then what other undiscovered cosmic megastructures might be lurking in the depths of space? One of the greatest challenges in studying this superstructure is determining its precise nature. Is it a physically connected formation, bound together by gravity, or is it simply an illusion created by the way we observe gamma ray bursts? If it is a true superstructure, then it must have formed through processes that defy our current understanding of cosmic structure formation. Gravity alone should not have been able to assemble such an enormous wall in the limited time since the Big Bang. This raises the possibility that additional forces, possibly even unknown physics, played a role in shaping the cosmos. A key aspect of this mystery involves the timeline of the universe's formation. According to the standard lambda cold dark matter model, galaxies and galaxy clusters form over billions of years, gradually assembling into the cosmic web we observe today. This model predicts that at very large scales, matter should be distributed relatively evenly, with only minor variations. The existence of a structure as vast as the Hercules-Corona Borealis Great Wall directly contradicts this expectation. Could it be that our models of cosmic evolution are missing a fundamental piece of the puzzle? One possibility is that dark matter played a more active role in the early universe than we currently assume. While dark matter is thought to interact with normal matter only through gravity, some theories suggest that it may have additional properties that could allow it to form structures on much larger scales. If dark matter can clump together in ways we do not yet understand, it might explain how a structure of this magnitude came into existence. Another hypothesis suggests that cosmic inflation, the rapid expansion of the universe in the first fraction of a second after the Big Bang, may have caused matter to be distributed unevenly on massive scales. Inflation theory predicts that quantum fluctuations in the early universe were stretched across vast distances, eventually forming the seeds of cosmic structure. If inflation had local variations in its intensity, it might have led to regions of extreme density, which could explain why some parts of the universe contain enormous superstructures while others remain relatively empty. There is also the question of whether we are seeing the entire structure. Given that the observable universe is limited by the speed of light, we can only detect objects whose light has had time to reach us. If the Hercules-Corona Borealis Great Wall is truly a singular formation, it might extend beyond what we can currently observe, meaning its full size could be even greater than we currently estimate. Future observations, possibly from next-generation space telescopes, may help determine whether the structure continues beyond our current field of view. The implications of this discovery also extend to the possibility of a multiverse. Some cosmologists have speculated that the presence of such a massive structure could be evidence of interactions between our universe and a neighboring one. If our universe once had a close encounter with another, it might have caused fluctuations in the distribution of matter, leading to the formation of such enormous cosmic walls. While this idea remains highly speculative, it is an intriguing possibility that could reshape our understanding of the fundamental nature of reality. Another potential explanation is that the Great Wall is a remnant of an ancient cosmic event, possibly related to the large-scale structure of the early universe. Some theories suggest that massive shockwaves or cosmic filaments may have influenced the distribution of matter billions of years ago, creating structures that persist to this day. If this is the case, then studying the Hercules-Corona Borealis Great Wall could provide insights into the earliest moments of cosmic history. To truly understand this cosmic giant, astronomers are turning to advanced observational techniques. Large-scale galaxy surveys, radio telescopes, and deep space infrared imaging are all being used to map the distribution of galaxies within the Great Wall. By analyzing the motion and composition of these galaxies, scientists hope to determine whether they are gravitationally bound, which would confirm that the structure is a genuine supercluster rather than a chance alignment of distant objects. One promising avenue of research involves using gravitational lensing, the bending of light by massive objects, to study the mass distribution within the Great Wall. If the structure contains large amounts of unseen dark matter, it should distort the light from background galaxies in a predictable way. By analyzing these distortions, astronomers can build a more accurate map of the structure and determine whether it truly qualifies as a gravitationally bound formation. Another approach involves studying the cosmic microwave background (CMB), the faint radiation left over from the Big Bang. If the Hercules-Corona Borealis Great Wall is as massive as it appears, it should have left an imprint on the CMB by altering the distribution of matter in the early universe. Scientists are analyzing high-resolution CMB data to look for subtle variations that could indicate the presence of such a massive structure. Despite the many unanswered questions surrounding the Hercules-Corona Borealis Great Wall, one thing is clear: its existence challenges our fundamental assumptions about the universe. If structures of this scale are more common than we currently realize, then we may need to rewrite our theories of cosmic evolution. Alternatively, if this is a unique anomaly, it could indicate that the conditions of the early universe were far more complex than we currently understand. The search for other structures of similar scale continues. If astronomers can identify additional cosmic megastructures, it may help determine whether the Hercules-Corona Borealis Great Wall is an isolated case or part of a larger pattern. Some researchers are already investigating potential candidates, analyzing deep space surveys for signs of similarly massive formations. As we push the boundaries of our observational capabilities, we may uncover new clues that help explain this incredible cosmic phenomenon. The next generation of telescopes, including the James Webb Space Telescope's successors and future radio astronomy arrays, will allow us to peer deeper into the universe than ever before. These advancements could provide the data needed to confirm whether the Hercules-Corona Borealis Great Wall is an unprecedented outlier or the first of many undiscovered cosmic giants. Ultimately, the existence of such an enormous structure forces us to confront one of the most profound questions in cosmology. Is the universe truly uniform on the largest scales, or are there hidden patterns and structures that we have yet to fully understand? If the latter is true, then our picture of the cosmos may be far more intricate and interconnected than we ever imagined. As we continue to explore the universe, the Hercules-Corona Borealis Great Wall stands as a symbol of the vastness of space and the limits of our current knowledge. It serves as a reminder that, despite all we have learned, the cosmos is still filled with mysteries waiting to be uncovered. With every new discovery, we take another step closer to unraveling the true nature of our universe and our place within it. The mystery of the Hercules-Corona Borealis Great Wall is not just a matter of size, it is a direct challenge to our understanding of the universe's evolution. If such a massive structure exists, it suggests that the cosmos is not as uniform as previously thought. This discovery raises profound questions. Could there be other, even larger structures hidden beyond our observable limits? Does this mean our understanding of the forces that shape the universe is incomplete? Could new physics be required to explain how such a massive structure could form in the time available since the Big Bang? To put this into perspective, our best cosmological models suggest that structures should only be able to grow to a certain size before the expansion of the universe smooths out any large-scale variations. The Standard Model of Cosmology, which incorporates dark matter and dark energy, predicts that matter should form into filaments and walls at a cosmic scale, but nothing as enormous as the Hercules-Corona Borealis Great Wall. If this structure truly exists as a gravitationally bound entity, it would defy these predictions and force us to rethink our understanding of large-scale cosmic structures. One of the most perplexing aspects of this discovery is the role of dark energy, the mysterious force responsible for the accelerated expansion of the universe. Current models suggest that as the universe expands, dark energy should dominate on the largest scales, preventing structures from forming beyond a certain size. Yet the Hercules-Corona Borealis Great Wall appears to defy this expectation, suggesting that either our understanding of dark energy is flawed or that it behaves differently at extreme scales. Another possibility is that the early universe contained density fluctuations far greater than current models predict. Cosmic inflation theory, which describes the rapid expansion of the universe moments after the Big Bang, suggests that tiny quantum fluctuations were stretched across vast cosmic distances, seeding the formation of galaxies and superclusters. If inflation behaved in an unexpected way, perhaps with certain regions expanding at different rates, it might have allowed for the formation of an ultra-large-scale structure like the Great Wall. To test this idea, scientists are analyzing the distribution of galaxies and gamma-ray bursts within the structure. If the galaxies are moving together in a coordinated way, this would indicate that they are gravitationally bound, confirming the Great Wall as a true structure rather than a statistical illusion. However, if the observed clustering is due to chance alignments in our line of sight, it might suggest that the Great Wall is not a single, cohesive entity but rather a collection of smaller structures. The challenge with detecting and verifying structures of this scale is the limitations of our observational tools. The universe is vast, and even with our most powerful telescopes, we can only observe a fraction of its entirety. Some scientists speculate that the Hercules-Corona Borealis Great Wall might extend beyond the observable universe, meaning we are only seeing a portion of its true size. If that is the case, then the full extent of this structure could be even more staggering than we currently estimate. The implications of this discovery go beyond cosmology and into the realm of fundamental physics. If a structure of this scale is possible, it could suggest the presence of unknown physical forces or interactions beyond the four fundamental forces we currently recognize: gravity, electromagnetism, and the strong and weak nuclear forces. Some radical theories even propose that such structures could be influenced by interactions between our universe and other parallel universes, a hypothesis that remains highly speculative but cannot yet be ruled out. Another major avenue of exploration involves studying the cosmic microwave background (CMB) for signs of the Great Wall's influence. The CMB is the afterglow of the Big Bang, and it provides a snapshot of the early universe. If the Great Wall had a significant impact on the distribution of matter, it should have left an imprint on the CMB. Scientists are analyzing high-resolution CMB data to look for subtle temperature variations that could provide clues about how this structure formed. One of the most mind-bending possibilities is that the Hercules-Corona Borealis Great Wall is not a gravitationally bound structure at all, but rather an observational artifact caused by the way we detect distant objects. Gamma-ray bursts, which were used to identify the structure, are among the most powerful explosions in the universe, but their distribution in space is not always straightforward. If there are biases in how we detect these bursts, it might create the illusion of a large structure where none actually exists. If the Great Wall is confirmed as a real cosmic structure, it would force a reconsideration of many fundamental assumptions about the universe. It could suggest that large-scale structures form more easily than we thought, or that certain regions of the cosmos evolved under very different conditions. It might even hint at new forces or interactions that operate on cosmic scales. Astronomers are now conducting follow-up observations to determine whether other structures of similar size exist elsewhere in the universe. If multiple ultra-large structures are found, it would suggest that our theories about the maximum size of cosmic structures are incorrect. On the other hand, if the Hercules-Corona Borealis Great Wall turns out to be a unique anomaly, it could indicate that something very unusual happened in that region of the universe's history. One of the most exciting aspects of this mystery is that we are only beginning to uncover the full picture. With next-generation telescopes such as the Square Kilometre Array, SK, and the upcoming advancements in deep space observations, we may soon have the ability to map cosmic structures in greater detail than ever before. These tools will allow scientists to probe the distribution of galaxies with unprecedented accuracy, potentially revealing new insights into the nature of the Great Wall and the forces that shaped it. At its core, the Hercules-Corona Borealis Great Wall represents the unknown, a frontier of cosmic exploration that challenges everything we think we understand about the universe. It is a reminder that even in an age of advanced science, there are still vast mysteries waiting to be uncovered. Every new discovery brings us closer to answering the biggest questions. How did the universe come to be? What forces shape its structure? And are we truly capable of understanding the full extent of the cosmos? As we continue our search for answers, the Hercules-Corona Borealis Great Wall stands as one of the most enigmatic and awe-inspiring discoveries in modern astronomy. Whether it turns out to be a true superstructure or an illusion created by our methods of observation, its presence forces us to question the limits of our knowledge and pushes us toward new scientific frontiers. The journey to understanding this cosmic giant is only beginning, and with every new observation, we take another step closer to unraveling one of the greatest space mysteries of all time. The search for answers about the Hercules-Corona Borealis Great Wall is not just an exercise in mapping the cosmos, it is a deep investigation into the fundamental nature of reality itself. If this structure is real, it forces astronomers to rethink the principles that govern the formation of large-scale cosmic structures. It could mean that the gravitational pull of dark matter, which acts as the scaffolding for galaxy formation, is stronger or behaves differently than we currently understand. Alternatively, it could suggest that dark energy, the mysterious force responsible for the accelerating expansion of the universe, is not as dominant as previously thought, or that it interacts in unexpected ways with massive structures. One of the key tools scientists use to study cosmic structures of this scale is redshift mapping. Redshift is the phenomenon where light from distant galaxies is stretched into longer wavelengths due to the expansion of the universe. By analyzing the redshift of thousands of galaxies, astronomers can determine their relative distances and construct three-dimensional maps of the universe. However, this method has its limitations. The accuracy of redshift measurements depends on the precision of the instruments used, and errors or biases in data collection could create artificial clustering effects that make a structure like the Great Wall appear larger than it truly is. This is why independent verification is crucial. Scientists are now using other methods, such as gravitational lensing, to test whether the mass distribution in the region of the Hercules-Corona Borealis Great Wall corresponds with the expected gravitational effects. Gravitational lensing occurs when a massive object, like a galaxy cluster, bends the light from more distant sources, creating distortions that can reveal hidden concentrations of mass. If the Great Wall is truly a massive structure, we should see clear lensing effects in its vicinity. Another method under consideration is the study of baryon acoustic oscillations, BAOs. These are subtle ripples in the distribution of galaxies, created by pressure waves in the early universe. BAOs serve as a cosmic ruler, helping astronomers measure large-scale structures with precision. If the Great Wall aligns with known BAO patterns, it would provide further evidence that it is a real, coherent structure rather than a statistical anomaly. One of the biggest challenges in understanding the Hercules-Corona Borealis Great Wall is the sheer scale of time involved. When we observe distant cosmic structures, we are looking back in time due to the finite speed of light. The light from these galaxies has traveled billions of years to reach us, meaning we are seeing them as they were long ago. This raises the question, is the Great Wall still intact today, Or has it evolved into a different form? Given the effects of cosmic expansion, gravitational interactions, and the potential influence of dark energy, the structure could have changed significantly over billions of years. The implications of this discovery extend beyond astrophysics and into the realm of theoretical physics. If a structure of this size can exist, it could provide new insights into the fundamental nature of space and time. Some researchers have even proposed that ultra-large cosmic structures could be linked to the fabric of space-time itself. In certain interpretations of string theory, for example, the universe may contain extra dimensions that influence the distribution of matter on cosmic scales. If these dimensions exist, they could play a role in the formation of structures like the Great Wall. Another controversial idea is that the Hercules-Corona Borealis Great Wall could be evidence of a multiverse, a collection of universes beyond our own. Some cosmological models suggest that if other universes exist, their interactions with our own could leave imprints in the large-scale structure of the cosmos. If the Great Wall is an unusually dense region of matter due to influences from another universe, it would revolutionize our understanding of reality and open up entirely new questions about the nature of existence. Regardless of the final explanation, the existence of the Hercules-Corona Borealis Great Wall is a profound reminder of how much we have yet to discover. Even with the most advanced telescopes and sophisticated theories, the universe continues to surprise us. This structure, whether it turns out to be a true supercluster or a complex observational illusion, challenges the very limits of what we thought possible. In the coming years, new space telescopes and observatories will provide even greater clarity. The Vera C. Rubin Observatory, set to begin operations soon, will conduct an unprecedented sky survey, capturing data on billions of galaxies and potentially revealing even larger structures. The James Webb Space Telescope, JWST, and other infrared observatories will allow us to peer deeper into the early universe, shedding light on how these massive structures came to be. If the Hercules-Corona Borealis Great Wall is confirmed as the largest structure in the universe, it will not only rewrite textbooks but also force physicists and cosmologists to reconsider some of the most fundamental assumptions about the cosmos. How do structures this large form in a universe governed by the laws of physics we understand? Are there unknown forces at play? Could this discovery hint at deeper, hidden aspects of reality that we have yet to uncover? As scientists continue their investigations, the mystery remains open. Each new discovery brings us closer to understanding the vast, complex web of cosmic structures that shape our universe. The Hercules-Corona Borealis Great Wall, whether an anomaly or a revelation, stands as a testament to the incredible scale and mystery of the cosmos. It is a reminder that, no matter how much we learn, the universe will always have secrets waiting to be uncovered. The implications of the Hercules-Corona Borealis Great Wall extend beyond astrophysics and into the very nature of cosmic evolution. If a structure of this magnitude truly exists, it means that our models of how matter organizes itself on the largest scales may be incomplete. One of the prevailing theories of cosmic structure formation is based on the lambda-cold dark matter model, which describes how dark matter and dark energy interact to shape the universe. However, the existence of a structure as large as the Great Wall would push the lambda-cold dark matter model to its limits, requiring modifications or entirely new physics to explain how such a colossal formation could have assembled in the time available since the Big Bang. One possible explanation is that cosmic structures can form hierarchically, merging over time into ever larger superstructures. Galaxies cluster together due to gravitational attraction, forming galaxy groups, then clusters, then superclusters. These superclusters themselves may align along vast filaments of the cosmic web, forming structures even larger than what our models currently predict. If the Hercules-Corona Borealis Great Wall is real, it may represent a natural extension of this hierarchy, but on a scale that defies previous expectations. However, there is also the question of whether such a massive structure should even exist within the observable universe. The cosmological principle, the assumption that, on large enough scales, the universe should look roughly the same in all directions, suggests that no single region should contain a structure vastly larger than others. If the Great Wall is an outlier in an otherwise homogeneous universe, it would challenge this foundational principle of cosmology. Another question that arises is whether the Great Wall is a truly connected structure or merely an apparent one. When dealing with cosmic structures spanning billions of light years, observational biases can sometimes create the illusion of large-scale formations where none actually exist. The large-scale distribution of galaxies in the region of the Great Wall could be influenced by selection effects in the data, uncertainties in distance measurements, or the inherent clustering tendencies of galaxies that make them appear more interconnected than they truly are. One method of testing the physical reality of the Great Wall is through velocity dispersion studies. If the galaxies within the Great Wall are part of a gravitationally bound system, they should exhibit coherent motion relative to each other. However, if they are merely coincidentally aligned along our line of sight, their velocities would be more random, indicating that they do not form a single, unified structure. Future observations using high-precision spectroscopic surveys will help clarify this issue. The study of cosmic voids, immense empty spaces between galaxy clusters, also plays a crucial role in understanding structures like the Great Wall. If the Great Wall exists as a true, coherent structure, then it should be accompanied by corresponding voids, where matter is significantly less dense. These voids act as the dark, empty spaces between the filaments of the cosmic web, defining the boundaries of massive structures. By mapping these voids in the region of the Great Wall, astronomers can determine whether it fits within the known framework of large-scale cosmic architecture or if it represents an entirely new category of structure. Another intriguing possibility is that the Great Wall may be connected to even larger, yet undiscovered structures. The observable universe is limited by the speed of light, meaning that we can only see objects whose light has had enough time to reach us since the beginning of cosmic expansion. If structures larger than the Great Wall exist beyond our current observational limits, they may influence the formation and distribution of galaxies within our visible universe. This could provide hints of a grander cosmic architecture, one that extends far beyond what we can currently detect. Furthermore, the discovery of the Great Wall has implications for our understanding of dark matter. The distribution of dark matter is thought to dictate the large-scale structure of the universe, forming an invisible framework upon which galaxies cluster. If the Great Wall is as massive as initial estimates suggest, then it may require an unprecedented concentration of dark matter to explain its formation. This could indicate that dark matter behaves differently on extremely large scales, or that our estimates of its influence need to be revised. In the search for answers, astronomers are turning to new observational techniques. Upcoming missions like the Euclid Space Telescope and the Nancy Grace Roman Space Telescope will provide deeper and more detailed maps of the cosmos, revealing structures previously hidden from view. These observations could confirm the existence of the Great Wall, refine our understanding of its dimensions, or even uncover new cosmic megastructures that rival its scale. If the Hercules-Corona Borealis Great Wall is eventually confirmed as the largest structure in the universe, it would have profound implications not only for astronomy but also for our broader understanding of the cosmos. It would challenge the limits of known physics, force revisions to our cosmological models, and open the door to new theories about the fundamental nature of reality. Whether it represents an extreme example of cosmic structure formation, a sign of unknown physics, or even a hint of something beyond our current understanding, its discovery is a testament to the boundless complexity of the universe. Ultimately, the study of the Great Wall is a reminder that, despite centuries of astronomical progress, we are still in the early stages of understanding the true nature of the cosmos. The universe remains full of mysteries, and as our technology and knowledge continue to advance, we may find that structures even larger, stranger, and more perplexing than the Hercules-Corona Borealis Great Wall are waiting to be discovered. If the Hercules-Corona Borealis Great Wall is real and as massive as initial studies suggest, it challenges one of the most fundamental assumptions of modern cosmology: the idea that the universe is homogeneous and isotropic on the largest scales. This assumption, known as the cosmological principle, states that, when viewed from a sufficiently large perspective, matter should be evenly distributed throughout the universe. However, a structure spanning tens of billions of light-years calls this principle into question. If the universe is not as uniform as we thought, then the fundamental equations governing cosmic evolution, such as Einstein's field equations of general relativity, may need to be revised to account for such large-scale variations. Some researchers have proposed that the Great Wall might not be a single continuous structure but rather a series of connected galaxy clusters and filaments that form an extended network. If this is the case, it could mean that we are observing not a single, gravitationally bound object but rather a region where galaxies are naturally aligning due to large-scale cosmic flows. However, if further studies confirm that the Great Wall is a true, single entity, it would be one of the most striking challenges to the lambda cold dark matter model of cosmology. One potential explanation for the Great Wall's existence could be the role of primordial density fluctuations. In the early universe, tiny variations in the density of matter, seeded by quantum fluctuations during the inflationary epoch, grew over billions of years into the vast structures we see today. If the Great Wall is real, it could be the result of an exceptionally high-density fluctuation in the early universe, leading to the accumulation of vast amounts of matter along a specific region of space. However, such an extreme fluctuation would be considered highly unlikely under our current understanding of inflationary cosmology. Another possibility is that the Great Wall represents a region where dark energy, the mysterious force driving the accelerated expansion of the universe, behaves differently than expected. Some alternative models of dark energy suggest that its effects may vary across the cosmos, leading to regions where gravitational structures can grow larger than usual. If this is the case, the Great Wall could provide indirect evidence of a fundamental flaw in our understanding of cosmic expansion. One of the most mind-bending hypotheses is that structures like the Hercules-Corona Borealis Great Wall could be linked to exotic physics beyond the standard model. Some speculative theories suggest that cosmic superstructures might be influenced by hidden dimensions or interactions with parallel universes. In certain models of string theory, for example, extraspatial dimensions could shape the way matter clusters on the largest scales, leading to structures that appear anomalously large from our three-dimensional perspective. Another speculative idea is that the Great Wall could be a cosmic imprint left behind by a previous phase of the universe. Some cyclic models of cosmology propose that the universe undergoes repeated cycles of expansion and contraction. If this is the case, massive structures like the Great Wall could be remnants of a past cosmic epoch, persisting across cycles of cosmic rebirth. While there is currently no direct evidence for such a model, discoveries like the Great Wall push the boundaries of what we consider possible, forcing us to entertain ideas once thought to be purely theoretical. Beyond theoretical physics, the existence of the Great Wall also has implications for our understanding of galactic evolution. If galaxies within the Great Wall formed in an environment with an exceptionally high density of matter, they may have unique properties compared to galaxies in less dense regions of the universe. Observing the chemical composition, star formation rates, and overall structure of galaxies within the Great Wall could reveal whether extreme large-scale structures influence the evolution of galaxies differently than in other parts of the cosmos. To fully understand the Great Wall, astronomers will need even more advanced observational tools. The upcoming Square Kilometre Array, SKA, a next-generation radio telescope set to be the largest ever built, will provide unparalleled insights into the distribution of matter in the universe. By mapping hydrogen gas across billions of light-years, SKA could reveal whether the Great Wall truly stands out as an independent structure or if it is part of a much larger network of cosmic filaments. Additionally, gravitational wave astronomy may offer new ways to probe the structure of the universe. If the Great Wall contains exceptionally massive galaxy clusters, their interactions could produce gravitational waves detectable by future observatories. These ripples in spacetime, first predicted by Einstein and confirmed in 2015, could provide another means of investigating the mass distribution and internal dynamics of the Great Wall. As we continue to refine our understanding of the universe, the Hercules-Corona Borealis Great Wall remains one of the most enigmatic and fascinating discoveries in modern astrophysics. Whether it is an extreme example of structure formation, a sign of physics beyond our current models, or a completely new phenomenon, it represents a profound mystery that could reshape our understanding of the cosmos. With each new technological breakthrough, we inch closer to unlocking the secrets of these vast cosmic structures. The Great Wall is a reminder that, despite centuries of scientific progress, the universe is still full of surprises, waiting for us to uncover its deepest truths. As astronomers peer deeper into the night sky, who knows what other colossal and mind-bending discoveries await? The discovery of the Hercules-Corona Borealis Great Wall is not just an isolated anomaly. It is part of a growing pattern of cosmic megastructures that defy our expectations. Over the years, astronomers have identified several other large-scale formations that push the boundaries of what we consider possible within the observable universe. These include the Sloan Great Wall, the Claus-Campusano LQG, Large Quasar Group, and the giant GRB ring, each of which challenges our assumptions about the limits of structure formation. However, the Hercules-Corona Borealis Great Wall remains the most extreme case, dwarfing all other known structures. One of the most pressing questions regarding the Great Wall is its true nature. Is it a single, gravitationally bound entity, or is it merely an illusion created by our observational methods? The problem arises from the way we detect such large-scale structures. The Great Wall was identified using gamma-ray bursts, GRBs, which serve as beacons from the distant universe. These immensely energetic explosions occur when massive stars collapse into black holes, sending out bursts of gamma radiation that can be detected across billions of light years. By mapping the distribution of these bursts, astronomers can infer the large-scale arrangement of matter in the cosmos. However, relying on GRBs to map cosmic structures comes with uncertainties. The distances to GRBs are estimated based on redshift measurements, which can sometimes introduce errors. If the distribution of GRBs in the Hercules-Corona Borealis region is affected by selection biases or statistical anomalies, it could create the illusion of a continuous structure where none actually exists. To confirm the existence of the Great Wall, independent observational techniques, such as galaxy surveys and radio telescopes, must corroborate the findings. If the Great Wall is real, then another major question arises: how did it form? The standard model of cosmology, based on the lambda cold dark matter framework, suggests that structures in the universe should have a maximum size limit, determined by the speed of light and the time available for matter to clump together since the Big Bang. The problem with the Hercules-Corona Borealis Great Wall is that its size appears to exceed this theoretical limit. In other words, there should not have been enough time in the 13.8 billion year history of the universe for such a massive structure to form under normal gravitational processes. One possibility is that the Great Wall formed from an unusually high-density region of the early universe, where matter accumulated more quickly than expected. If this is the case, then studying the Great Wall could provide valuable insights into the conditions of the universe shortly after the Big Bang. Some theories suggest that quantum fluctuations during the inflationary epoch, when the universe expanded exponentially in the first fraction of a second, could have seeded these massive structures. If an exceptionally large fluctuation occurred in the region that became the Great Wall, it might explain why such an enormous structure exists today. Another possibility is that the Great Wall is not a true structure in the traditional sense but rather a statistical alignment of galaxy clusters and filaments that only appear connected from our vantage point. In this scenario, the individual clusters within the Great Wall may not be gravitationally bound to each other, meaning that over cosmic timescales, they will drift apart due to the ongoing expansion of the universe. If this is the case, the Great Wall may not be a permanent feature of the cosmos but rather a temporary alignment that will gradually dissipate over billions of years. A more radical hypothesis is that the Great Wall hints at physics beyond our current understanding. Some theories propose that dark energy, the mysterious force responsible for accelerating the expansion of the universe, may not be uniform across space. If dark energy varies in strength depending on location, it could create regions where cosmic structures grow larger than expected. This idea, while speculative, could provide an alternative explanation for why we observe structures like the Great Wall. Additionally, the study of the Great Wall could have implications for the nature of dark matter. Dark matter, which makes up roughly 85% of the matter in the universe, is thought to play a crucial role in structure formation. If the Great Wall contains an unusually high concentration of dark matter, it could provide clues about the properties of this elusive substance. By mapping the distribution of dark matter in the region, astronomers may gain new insights into how it influences the large-scale structure of the universe. The potential existence of the Hercules-Corona Borealis Great Wall also raises profound philosophical questions about the nature of the cosmos. If the universe contains structures far larger than we previously thought possible, it could suggest that our understanding of cosmic evolution is incomplete. Some researchers have even speculated that such megastructures could be evidence of deeper underlying patterns in the fabric of spacetime itself. Could the universe contain hidden symmetries or geometric principles that govern the arrangement of matter on the grandest scales? Furthermore, if structures like the Great Wall continue to be discovered, it could hint at the possibility that our observable universe is only a small part of a much larger and more complex reality. Some cosmological models suggest that the universe extends far beyond what we can see, potentially containing even larger structures that remain hidden from our view. If this is the case, then the Hercules-Corona Borealis Great Wall may be just one piece of a vast cosmic puzzle that we are only beginning to unravel. Looking ahead, future astronomical surveys will play a critical role in determining the true nature of the Great Wall. The Vera C. Rubin Observatory, set to begin operations in the coming years, will conduct an unprecedented deep sky survey that could provide new insights into the structure of the universe. By mapping the distribution of galaxies with unparalleled precision, it may confirm or refute the existence of the Great Wall, helping to resolve one of the most pressing mysteries in cosmology. Additionally, next-generation space telescopes, such as the James Webb Space Telescope, JWST, and the planned Habitable Worlds Observatory, could shed light on the environments within the Great Wall. If galaxies in this region exhibit unusual properties, it could provide further evidence that the Great Wall is a unique and significant feature of the cosmos. Regardless of the final outcome, the study of the Hercules-Corona Borealis Great Wall represents a major step forward in our quest to understand the universe. Whether it is an extreme example of structure formation, a statistical illusion, or a sign of unknown physics, it forces us to confront the limits of our knowledge and challenge our most fundamental assumptions about the cosmos. As technology advances and our observational capabilities improve, we may eventually uncover the true nature of the Great Wall and its place in the grand cosmic web. But for now, it remains one of the greatest mysteries of the universe, an enigma that continues to inspire awe and curiosity among astronomers and cosmologists alike. The mystery of the Hercules-Corona Borealis Great Wall is more than just a question of size. It is a fundamental challenge to our understanding of how the universe works. If this structure is real and truly as vast as current estimates suggest, it may force scientists to reconsider some of the core principles of cosmology, including the way matter organizes itself on the grandest scales. It also raises the question of whether such structures are unique, or if even larger ones exist beyond the limits of our current observational technology. One of the key implications of the Great Wall is its potential impact on the cosmological principle, which states that on large enough scales, the universe should appear roughly the same in all directions. This principle is the foundation of modern cosmology, guiding theories about the structure and evolution of the cosmos. However, the existence of a structure as immense as the Hercules-Corona Borealis Great Wall would seem to contradict this assumption. It would mean that the universe is not as uniform as we believed and that matter can clump together on scales far larger than previously thought possible. If the cosmological principle is violated, it could have profound consequences for our understanding of the Big Bang and the large-scale evolution of the universe. The distribution of galaxies and galaxy clusters is supposed to follow predictable patterns, influenced by gravity, dark matter, and the expansion of the universe. However, the Great Wall's sheer size suggests that something else may be at play, perhaps an unknown force or process that allows such massive structures to form. This raises the possibility that there are hidden aspects of cosmic evolution that current models fail to explain. One potential explanation for the Great Wall's existence lies in the physics of inflation, the brief period of rapid expansion that occurred in the first fraction of a second after the Big Bang. During inflation, tiny quantum fluctuations were stretched across vast cosmic distances, seeding the formation of galaxies and large-scale structures. If inflation created irregularities on much larger scales than expected, it could explain why we observe structures like the Great Wall. Some theorists even suggest that these irregularities could be remnants of physics from a previous universe, hinting at a deeper cosmic cycle beyond the Big Bang itself. Another avenue of research involves investigating the role of dark matter in the formation of the Great Wall. Dark matter is believed to be the scaffolding upon which galaxies and cosmic structures form, providing the unseen gravitational framework that binds clusters together. If the Great Wall contains an unusually high concentration of dark matter, it could offer clues about the nature of this mysterious substance. Some alternative theories propose that dark matter is not evenly distributed throughout the universe, but rather forms large filaments and voids that create extreme cosmic structures. If true, the Great Wall could be one of the largest manifestations of this phenomenon. Observations of the Great Wall also raise questions about how structures interact on cosmic scales. If it is truly a coherent entity, does it exert gravitational influence over its surroundings? Could it distort the motion of nearby galaxies, altering their paths over billions of years? If so, studying the Great Wall could provide a unique laboratory for understanding how gravity operates across the largest distances in the universe. Additionally, the Great Wall could have implications for our understanding of cosmic expansion. The standard model of cosmology suggests that the universe is expanding at an accelerating rate due to dark energy. However, if structures like the Great Wall can resist this expansion, it may suggest that dark energy behaves differently in certain regions of the cosmos. Some researchers have proposed that dark energy is not a uniform force but rather a dynamic phenomenon that varies in strength over time and space. If this is the case, it could change our entire perspective on the fate of the universe. Another intriguing possibility is that the Great Wall represents a form of cosmic architecture that follows unknown principles. Some physicists have speculated that the distribution of galaxies is not random but follows deeper mathematical patterns that we have yet to fully understand. If the Great Wall fits into a larger, hidden structure of the cosmos, it could hint at underlying symmetries in spacetime itself. This idea is speculative but not entirely implausible. Some cosmological models predict that large-scale structures could follow fractal-like patterns or other geometric rules that extend beyond our current theories. The existence of the Great Wall also has potential implications for the search for extraterrestrial intelligence. If intelligent civilizations exist in the universe, it is possible that they, too, would be influenced by the large-scale structure of the cosmos. Some researchers have suggested that galactic superstructures could act as cosmic highways for interstellar civilizations, providing dense regions of matter where advanced life might thrive. While purely hypothetical, this idea raises the question of whether megastructures like the Great Wall could play a role in shaping the long-term development of intelligent life on a cosmic scale. Despite the many questions surrounding the Hercules-Corona Borealis Great Wall, one thing is clear: it represents a significant challenge to our understanding of the universe. Whether it is a true physical structure, a statistical anomaly, or a sign of unknown physics, its discovery forces scientists to rethink the limits of cosmic evolution. Future observations will be crucial in determining its true nature, but for now, it remains one of the most perplexing and awe-inspiring mysteries of the cosmos. As astronomers continue to refine their techniques and explore the depths of space with more powerful telescopes, we may one day unravel the secrets of the Great Wall and other vast cosmic structures. Until then, it serves as a reminder that the universe is far more complex and enigmatic than we ever imagined, a vast cosmic puzzle waiting to be solved. The Hercules-Corona Borealis Great Wall is more than just an anomaly. It is a direct challenge to the very fabric of our understanding of the universe. The deeper we investigate its existence, the more it forces us to confront fundamental questions about how cosmic structures form, how gravity operates on the grandest scales, and whether the universe is as uniform as we once believed. The fact that such a massive structure could persist for billions of years suggests that our current models may be incomplete, and perhaps, hidden forces or unknown aspects of physics are at play. One of the most perplexing aspects of the Great Wall is how it fits within the timeline of cosmic evolution. The universe is approximately 13.8 billion years old, and the formation of such an enormous structure should, in theory, require an immense amount of time. Yet, given the vast distances involved, it suggests that galaxies within this superstructure must have interacted gravitationally over billions of years, forming a cosmic web unlike anything previously observed. This raises the question, how did it form so quickly? Did it emerge from a unique region of the early universe where matter distribution was fundamentally different from other areas? Or does it indicate that the laws governing large-scale structure formation are not as uniform as we assumed? The scale of the Great Wall also challenges our understanding of how matter clusters in the universe. According to the lambda cold dark matter model, the leading framework in cosmology, the formation of large-scale structures is driven by dark matter, which forms a cosmic web that ordinary matter follows. However, the existence of such a massive structure suggests that either dark matter behaves in unexpected ways or that additional forces influenced its formation. If dark matter is distributed in a way that allows for structures as immense as the Great Wall, it could imply that dark matter itself has more complex interactions than previously thought. Some researchers speculate that dark matter may not be a single type of particle but rather a collection of different types of unknown particles that interact differently under certain conditions. Furthermore, the Great Wall's presence raises questions about the large-scale topology of the universe. Some theories suggest that the cosmos may have regions of extreme clustering, separated by immense voids where very little matter exists. If this is the case, it could indicate that the universe is not as isotropic as the cosmological principle suggests. Instead of being evenly distributed, matter may be arranged in patterns far more intricate than we currently understand, forming a vast cosmic tapestry that defies conventional explanations. The study of cosmic voids, the empty spaces between massive structures, may provide additional clues about the nature of the Great Wall. These voids are often thought to be the result of gravitational interactions that pull matter into large clusters, leaving behind empty expanses. However, if the Great Wall is part of a larger, organized system of voids and filaments, it could indicate that the universe follows a structured pattern that extends far beyond our observational limits. Some physicists propose that these patterns may be the result of quantum fluctuations in the early universe, which could have imprinted a fractal-like structure on the cosmos, influencing the distribution of galaxies on the largest scales. Another possibility is that the Great Wall is a remnant of an earlier phase of cosmic history, potentially linked to unknown physical processes that occurred shortly after the Big Bang. If certain regions of the universe experienced different rates of expansion or different distributions of dark matter, it could have led to the formation of extreme structures like the Great Wall. Some alternative cosmological models, such as those involving cyclic universes or variations in the fundamental constants of physics, suggest that different regions of space could have evolved under different conditions. If so, the Great Wall might not be an anomaly at all but rather a clue pointing toward a deeper, hidden order in the cosmos. Observationally, studying the Great Wall poses a significant challenge. Due to its enormous size, it spans across multiple regions of the sky, making it difficult to analyze as a single entity. Moreover, because it is located so far away, much of the light we observe from its galaxies has traveled for billions of years, meaning we are seeing it as it existed in the distant past. This raises an intriguing question. What does the Great Wall look like today? Has it changed, expanded, or become even more complex over time? If we could observe its present state, it might provide invaluable insights into how such structures evolve over cosmic time. The presence of the Great Wall also has implications for our understanding of the ultimate fate of the universe. If structures this large can form, it suggests that the universe's expansion may not be as simple as previously thought. Some models propose that cosmic expansion could be uneven, with certain regions experiencing different rates of growth due to the distribution of dark energy. If dark energy behaves differently in different parts of the universe, it could mean that structures like the Great Wall act as gravitational anchors, slowing down expansion in some regions while allowing others to accelerate. This idea is still speculative, but if true, it could change our perspective on the long-term evolution of the cosmos. In addition, the Great Wall's discovery raises the possibility that even larger structures may exist beyond our current observational limits. The observable universe is only a fraction of the total cosmos, what lies beyond could be even more extraordinary. If structures larger than the Great Wall exist, they could fundamentally reshape our theories about cosmic evolution and the scale at which order emerges from the chaos of the Big Bang. Some theories even suggest that the distribution of matter in the universe may extend into dimensions beyond the three we experience, meaning that structures like the Great Wall could be part of a much larger, multidimensional framework that we have yet to perceive. Ultimately, the Hercules-Corona Borealis Great Wall remains one of the most perplexing and awe-inspiring discoveries in modern cosmology. Whether it is an extreme statistical fluke, an indication of unknown physical processes, or evidence of a deeper cosmic architecture, its presence forces us to rethink the very foundations of our understanding of the universe. Future research will be crucial in determining its true nature, and with advancements in observational technology, such as the upcoming next-generation telescopes, we may one day uncover the secrets of this colossal structure. Until then, the Great Wall stands as a monument to the vastness of the cosmos, reminding us that no matter how much we think we understand, the universe always has more mysteries waiting to be revealed. Its discovery is not just a scientific puzzle but a testament to the boundless curiosity that drives humanity to explore the unknown. The mystery of the Hercules-Corona Borealis Great Wall deepens as we consider its implications on fundamental physics. If structures this vast can exist, we must reconsider whether the cosmological principle, the idea that the universe is roughly uniform when viewed on a large scale, holds true. The existence of the Great Wall suggests that matter in the universe may be arranged in a way that defies our expectations, challenging the assumption that no region should be significantly different from another when averaged across vast distances. If this assumption is incorrect, then our entire approach to modeling the universe may need to be revised. One of the key questions that arise from this discovery is whether the Great Wall is a singular anomaly or part of a greater, interconnected cosmic web. Some astronomers speculate that there may be even larger structures beyond our observable limits, hinting at a universe far more structured than we currently comprehend. If we were to extend our reach and discover other superstructures of similar or greater magnitude, it would suggest that the universe is not only more complex but also potentially infinite in its variation of large-scale formations. This also brings up the issue of dark energy and its role in shaping the universe. Dark energy is thought to be responsible for the accelerating expansion of the cosmos. But if such massive structures are forming, it could indicate that dark energy is not as uniformly distributed as previously thought. Instead of acting as a smooth force pushing galaxies apart at a constant rate, dark energy might interact differently in regions where enormous mass concentrations exist. This could mean that the Great Wall and similar formations are acting as local counterforces to cosmic expansion, creating gravitational wells that subtly affect the rate at which different parts of the universe expand. Moreover, the Great Wall's structure itself presents a challenge in terms of galaxy clustering. Under the standard model of cosmology, galaxies are expected to group together in clusters and superclusters, but they should not form vast, interconnected walls spanning billions of light years. The discovery of this structure raises the question of whether our understanding of how galaxies interact gravitationally on the largest scales is correct. Are there hidden forces guiding these formations? Could there be yet undiscovered interactions between galaxies beyond simple gravitational attraction? One possible explanation is that the Great Wall is a relic of an ancient cosmic event that influenced galaxy distribution on a grand scale. Some researchers speculate that immense shockwaves from the early universe, possibly caused by interactions between different regions of space, could have played a role in shaping these superstructures. If true, the Great Wall could be a fossil imprint of an event that occurred shortly after the Big Bang, offering a window into the earliest moments of cosmic history. Another possibility involves exotic physics, including the idea that the distribution of dark matter and dark energy is not as we currently model it. If dark matter clumped together in unexpected ways during the formation of the early universe, it might have created gravitational scaffolding that allowed for the development of structures far larger than expected. Alternatively, some scientists propose that modifications to gravity itself may be needed to explain the existence of the Great Wall. If gravity behaves differently at cosmic scales, it could allow for the formation of immense structures that our current equations do not predict. The implications of these ideas extend beyond astrophysics and into fundamental physics, challenging our understanding of the fundamental forces that govern reality. If the Great Wall is evidence that gravity or dark matter behaves differently than expected, it could provide clues toward a long-sought theory of quantum gravity, a unified framework that merges Einstein's general relativity with quantum mechanics. Some theorists suggest that large-scale cosmic structures like the Great Wall could be influenced by quantum effects on an unimaginable scale, hinting at a deeper, hidden structure to the fabric of spacetime itself. There is also the possibility that the Great Wall is an indication of a larger cosmic cycle, in which structures form and dissolve over vast timescales. Some cosmological models propose that the universe undergoes repeated cycles of expansion and contraction, with each cycle leaving behind imprints in the form of superstructures like the Great Wall. If this theory is correct, then the Great Wall could be one of many such remnants from previous cosmic epochs, pointing toward a universe with a history far longer and more complex than we currently assume. The biggest challenge in studying the Great Wall is its sheer distance from us. Because we are observing light that has traveled for billions of years, we are essentially looking back in time. This raises the question, what does the Great Wall look like in the present? Has it continued to grow, or have parts of it fragmented due to cosmic expansion? If we could somehow observe its current state, it might provide valuable insights into the long-term evolution of such structures. Future telescopes, such as the upcoming Extremely Large Telescope, ELT, and the James Webb Space Telescope's successors, may offer a clearer picture of the Great Wall's structure and composition. By analyzing the precise redshifts of galaxies within the Great Wall, astronomers hope to determine whether its formation followed known physical laws or if it points to unknown cosmic processes. If deviations are found, they could be the first signs that new physics is at play, opening the door to revolutionary discoveries about the nature of the universe. There is also the possibility that the Great Wall is connected to other structures we have yet to fully map. If this is the case, it could indicate that the observable universe is part of an even larger, interconnected system of walls, voids, and filaments. Some theorists even suggest that these structures may follow a fractal pattern, meaning that similar patterns repeat at different scales throughout the cosmos. If true, this could provide insights into whether the universe has an underlying order that extends far beyond what we currently perceive. One of the most fascinating aspects of the Great Wall's discovery is that it reminds us of how little we truly know about the universe. Despite our advances in technology and theoretical physics, we continue to uncover structures and phenomena that challenge our models and force us to rethink fundamental assumptions. The Great Wall is not just a testament to the vastness of the cosmos, it is a direct challenge to our understanding of how the universe is built. As we continue to investigate this colossal structure, we may find answers that reshape our understanding of cosmology, physics, and the nature of reality itself. Whether the Great Wall is an outlier or the first of many similar discoveries, it has already left an indelible mark on our quest to comprehend the cosmos. And perhaps, as we refine our observational tools and theoretical models, we will one day uncover the ultimate explanation for the existence of structures so vast that they seem to defy the very limits of the universe itself. The search for an explanation behind the Hercules-Corona Borealis Great Wall is one of the most perplexing and ambitious undertakings in modern astrophysics. Its sheer size, spanning over 10 billion light-years, forces us to rethink our understanding of cosmic evolution, structure formation, and even the fundamental nature of the universe. If such an enormous structure can exist, what else might be out there that we have yet to discover? Could there be structures even larger than the Great Wall, hidden just beyond the limits of our observable universe? One of the most compelling possibilities is that the Great Wall is a piece of a much larger, interconnected network of cosmic structures, forming a vast web that stretches beyond what we can currently see. If this is the case, then our universe may be far more ordered and structured on the grandest scales than we have ever imagined. Some researchers suggest that the universe itself may follow fractal patterns, meaning that similar structures repeat at different scales. If this theory holds, then the Great Wall could be one of many repeating cosmic formations, each playing a role in shaping the large-scale geometry of the cosmos. This idea leads to an even deeper mystery. Why do such massive structures exist at all? The standard model of cosmology, which describes how the universe evolved from the Big Bang to its current state, suggests that structures should not grow beyond a certain size due to the expansion of space. Yet, the existence of the Great Wall contradicts this expectation, raising questions about whether our understanding of cosmic inflation and dark energy is incomplete. One possibility is that the distribution of dark energy is not as uniform as we assume. Dark energy is thought to be responsible for accelerating the expansion of the universe, but if it varies across different regions of space, it could lead to the formation of superstructures on a previously unimagined scale. If dark energy pools or concentrates in certain areas while remaining weaker in others, it might create gravitational wells that allow for the emergence of immense formations like the Great Wall. Another alternative is that the Great Wall is a remnant of an ancient cosmic event, possibly dating back to the early moments of the universe. Some theories propose that shockwaves from primordial cosmic collisions, or even interactions between different regions of the universe, could have left behind large-scale imprints in the form of galaxy superstructures. If this is true, then the Great Wall may be a relic of an event that predates even the formation of galaxies themselves. But what if the Great Wall is not just a naturally occurring phenomenon? Some of the more speculative theories suggest that structures of this magnitude could be evidence of unknown forces or even artificial cosmic engineering on a scale beyond human comprehension. Could an advanced extraterrestrial civilization, billions of years older than our own, have had a hand in shaping the universe on a grand scale? While this idea may sound like science fiction, it is not entirely outside the realm of possibility. The concept of Kardashev Type 3 civilizations that manipulate entire galaxies or even galaxy clusters for energy, suggests that, if such beings exist, they might leave behind colossal structures as signatures of their activity. Whether natural or artificial, the Hercules-Corona Borealis Great Wall remains one of the most significant cosmic puzzles ever encountered. The biggest challenge in studying it is its immense distance from Earth. Because light from the Great Wall has traveled for billions of years to reach us, we are seeing it as it was in the distant past. But what does it look like now? Has it grown even larger, or has it started to fragment due to the expansion of the universe? Answering these questions will require next-generation telescopes capable of mapping the universe with unprecedented precision. The upcoming Extremely Large Telescope, ELT, and future space observatories may provide the tools necessary to analyze the Great Wall in more detail. By measuring the precise redshifts of galaxies within the structure, astronomers hope to determine whether its formation follows known physical laws or if it hints at entirely new cosmic processes. But even if we unlock the secrets of the Great Wall, it may be only the beginning of an even greater mystery. If one structure of this scale can exist, there may be others waiting to be discovered. Could we be on the verge of a paradigm shift in our understanding of the cosmos, one that reveals an even deeper layer of structure hidden within the universe? As we push the boundaries of our knowledge further, the Hercules-Corona Borealis Great Wall serves as a reminder of just how little we truly understand about the cosmos. It challenges our theories, defies our expectations, and forces us to confront the vast, unexplored depths of space with a renewed sense of curiosity and wonder. And perhaps, in our continued search for answers, we will uncover new cosmic truths that redefine our place in the grand tapestry of the universe. If the Hercules-Corona Borealis Great Wall is not an anomaly but a clue to a larger cosmic pattern, then our understanding of the universe may need to be fundamentally revised. Theories that once seemed unshakable, such as the uniformity of large-scale cosmic structure, may have to be reconsidered in light of this massive formation. But if the Great Wall is just one of many such structures, then what does that tell us about the true nature of the universe? Could it be that we are only seeing a fraction of an interconnected system far grander than we ever imagined? Some physicists propose that the universe itself may be structured in a way that defies conventional explanations. Instead of being an evenly distributed web of galaxies, it could contain vast walls, voids, and filaments that emerge from deeper, hidden physical laws. If so, the presence of the Great Wall might not be an exception but rather a confirmation of an as yet unknown rule governing cosmic evolution. One radical idea suggests that the universe may be arranged according to principles found in higher dimensional space. In this scenario, the Great Wall could be a three-dimensional projection of a larger, multidimensional structure. If true, then what we are seeing may only be a shadow of a reality that extends beyond our perception, hinting at the possibility that the universe itself may be far more complex than we currently assume. The study of cosmic structures like the Great Wall is also deeply connected to the mystery of dark matter. Galaxies within the Great Wall are bound together in ways that suggest the presence of an unseen gravitational force. Standard models of cosmology account for this by proposing the existence of dark matter, a mysterious substance that makes up most of the universe's mass yet remains undetectable by conventional means. Could the Great Wall be telling us something new about dark matter? Some researchers speculate that structures of this scale may be influenced by interactions between dark matter and ordinary matter in ways we do not yet fully understand. If dark matter has properties that allow it to form large-scale filaments stretching across billions of light years, it might explain why formations like the Great Wall exist. Alternatively, the distribution of dark matter itself may be shaped by forces beyond our current comprehension, meaning that the Great Wall could be a window into new physics waiting to be discovered. Another profound mystery surrounding the Great Wall is its apparent defiance of the cosmic horizon. The cosmic horizon is the theoretical limit beyond which light has not had time to reach us since the beginning of the universe. If structures as massive as the Great Wall exist close to this horizon, it raises questions about whether even larger formations may lie beyond our ability to detect them. Could it be that what we see is just a small section of an even more extensive cosmic landscape, one that stretches far beyond what our telescopes can observe? Some theorists suggest that the existence of such vast structures might support the idea of a cyclic universe, in which cosmic structures persist across multiple phases of cosmic expansion and contraction. In this model, massive walls like Hercules-Corona Borealis may not be recent formations but instead remnants of previous cosmic cycles, carrying forward imprints from earlier epochs of universal history. If this is true, then studying the Great Wall may provide evidence for a much older, recurring pattern of cosmic evolution, one in which the universe undergoes endless cycles of rebirth. Another question that arises from the Great Wall's existence is whether it could have had any effect on cosmic background radiation. The cosmic microwave background (CMB) is the faint afterglow of the Big Bang, and it serves as one of our most critical tools for understanding the early universe. If the Great Wall is indeed a product of early cosmic evolution, it might have left subtle imprints on the CMB that we have yet to detect. Future telescopes capable of mapping the CMB in even greater detail may provide crucial insights into whether structures like the Great Wall influenced the formation of the universe itself. Despite all of these theories, one undeniable fact remains: the Hercules-Corona Borealis Great Wall is a mystery that challenges everything we thought we knew about the cosmos. It stands as a colossal question mark in our understanding of physics, dark matter, cosmic structure, and even the fundamental nature of space and time. Whether it is a relic of a past cosmic event, evidence of new physics, or a sign of an even larger pattern that we have yet to uncover, one thing is certain: it has changed the way we see the universe forever. The search for answers continues, and with every new telescope, simulation, and observation, we move one step closer to unraveling the full story behind the Great Wall. Perhaps the coming decades will bring discoveries that force us to rewrite our theories, introducing new physics that explain not just the Great Wall but the deepest workings of the cosmos itself. And if we do find those answers, they may be far stranger than anything we can currently imagine. The Hercules-Corona Borealis Great Wall remains one of the most baffling and awe-inspiring discoveries in modern astrophysics. Its very existence stretches the limits of our understanding, defying the conventional models that dictate how cosmic structures should form and evolve. If this enormous galactic wall is real, then it forces us to confront an even deeper question: what does it reveal about the ultimate structure of the universe? For decades, astronomers have worked under the assumption that on the largest scales, the universe is homogeneous and isotropic, meaning that matter should be roughly evenly distributed in all directions. This assumption, known as the cosmological principle, is a cornerstone of modern cosmology. Yet, The Hercules-Corona Borealis Great Wall appears to challenge this idea directly. If structures of such scale can exist, then perhaps the universe is not as uniform as we once believed. This could have profound implications for everything from dark matter distribution to the ultimate fate of the cosmos itself. One possible explanation for the Great Wall's existence is that it represents a remnant of an earlier phase in cosmic evolution, a structure that formed when the universe was still young and denser regions clumped together under the influence of gravity. If this is the case, then studying the Great Wall could provide a rare glimpse into how the earliest cosmic structures were formed, offering critical clues about the forces that shaped the universe in its infancy. However, another theory suggests that the Great Wall may not be a single, continuous structure but rather a complex, interconnected web of galaxy clusters that only appear to form a massive wall due to our observational limitations. If true, this could mean that the structure is not a challenge to physics but rather a reflection of how galaxies naturally cluster together over time. But even if this is the case, the sheer scale of the formation remains difficult to explain within standard cosmological models. One of the most striking aspects of the Great Wall is its potential relationship with cosmic voids, vast, empty regions of space that contain little to no galaxies. These voids play a crucial role in the large-scale structure of the universe, acting as the negative space between superclusters and filaments. Some scientists speculate that the presence of such a massive structure could indicate a corresponding void of equal or greater magnitude, a region of space so empty that it further exaggerates the prominence of the Great Wall. If such a void exists, it could provide further insight into how matter is distributed on the grandest scales. The Great Wall also raises questions about how structures like it could persist over billions of years despite the accelerating expansion of the universe. Under the influence of dark energy, galaxies are gradually being pushed apart at ever-increasing speeds. If the Great Wall has managed to maintain its structure despite this relentless expansion, it suggests that the gravitational forces within it must be exceptionally strong. This could indicate the presence of enormous quantities of dark matter, a mysterious substance that does not emit light but exerts gravitational influence. If dark matter plays a role in holding the Great Wall together, then studying this structure could offer crucial clues about the nature of this elusive component of the universe. Current models suggest that dark matter forms a cosmic scaffolding upon which galaxies and galaxy clusters are built. If the Great Wall is anchored within an especially dense region of dark matter, it could provide one of the strongest pieces of evidence yet that dark matter serves as the backbone of cosmic structure formation. Another possibility is that the Great Wall is not an isolated structure but rather part of an even larger, interconnected web that extends far beyond what we can currently observe. If this is true, then the Hercules-Corona Borealis Great Wall may be just one segment of a far more extensive cosmic architecture, one that stretches across distances too vast for us to comprehend. If we assume that the Great Wall is not an anomaly but rather a part of a larger pattern, then what might this pattern be? Some cosmologists have speculated that the universe could be structured in a way that resembles a fractal, meaning that similar patterns repeat at different scales. If this idea holds, then the Great Wall may not be unique. It could be one of many repeating formations that exist throughout the cosmos. But if the universe does follow fractal-like structures, then it raises even more questions. What is driving this pattern? Is there an underlying set of physical laws that naturally produces such formations, or is it the result of an unknown force? Could there be structures even larger than the Great Wall, stretching beyond the observable limits of our universe? Perhaps the most unsettling possibility is that our entire understanding of cosmic evolution is incomplete. If structures as massive as the Great Wall can exist, then our current models of galaxy formation and gravitational interaction may be missing a crucial piece of the puzzle. This could mean that the physics we currently accept as fundamental, such as the role of dark matter, the behavior of gravity on cosmic scales, or even the very nature of space-time itself, may need to be re-examined. To answer these questions, astronomers are developing new techniques for studying the universe on the largest scales. Future telescopes, such as the Vera-C, Rubin Observatory and the next generation of space-based instruments, will allow us to map the cosmos in greater detail than ever before. By observing more distant galaxies and refining our understanding of cosmic structure, we may finally uncover the truth behind the Hercules-Corona Borealis Great Wall. Yet, for all the technology and theories we develop, the Great Wall remains an enigma. It is a reminder that the universe is still full of mysteries, some of which may be beyond our ability to fully comprehend. It forces us to confront the limits of our knowledge and challenges us to keep pushing forward in our search for answers. As we continue to explore the cosmos, we must ask ourselves, if we have already found a structure as vast as the Great Wall, what other secrets remain hidden in the depths of space? Are we only beginning to scratch the surface of a much larger, more intricate cosmic landscape? And if so, what revelations await us in the vast, uncharted territories of the universe? Perhaps the answer lies just beyond our current reach, waiting for the next generation of explorers to uncover. Until then, the Hercules-Corona Borealis Great Wall stands as one of the greatest unsolved mysteries of the cosmos, a colossal testament to the vastness and complexity of the universe we call home. The Hercules-Corona Borealis Great Wall stands as a silent titan in the cosmic landscape, stretching across billions of light years, defying our expectations and forcing us to confront the possibility that our understanding of the universe is still woefully incomplete. If structures like this can exist, then what else might be out there, lurking beyond our observational limits? Could there be even larger formations, ones that make even this Great Wall seem insignificant by comparison? And if so, how do they fit into the grand design of the cosmos? Some astrophysicists speculate that the Great Wall might not be an isolated phenomenon but instead part of a much larger and interconnected cosmic framework, one that stretches beyond what we can currently observe. If true, then the observable universe may only be a fraction of a far greater cosmic structure, an intricate network of walls, filaments, and voids that extend beyond even our most powerful telescopes. One of the most perplexing questions is how such a colossal structure could have formed in the first place. Current models of cosmic evolution suggest that the universe began as a nearly uniform soup of particles after the Big Bang, with only tiny fluctuations in density. Over time, gravity amplified these fluctuations, pulling matter together to form galaxies, clusters, and superclusters. But a structure as massive as the Hercules-Corona Borealis Great Wall should have required an extraordinary amount of time to form, longer, perhaps, than the universe has even existed. This apparent paradox leads some researchers to consider the possibility that our understanding of cosmic evolution is incomplete. Could it be that there are unknown forces at work, shaping the large-scale structure of the universe in ways we do not yet understand? Could the Great Wall be a relic from an earlier cosmic epoch, a remnant of a universe that existed before our own? Some cosmologists have proposed that vast structures like the Great Wall may be evidence for a cyclic universe, one in which the cosmos undergoes repeated cycles of expansion and contraction. In this model, each new universe inherits certain large-scale structures from the previous one, much like how geological features on Earth persist across multiple eras. If this theory is correct, then the Great Wall might not be a recent formation at all, but instead a relic from a previous cosmic age, providing us with a direct glimpse into the deep history of the universe. Another theory suggests that the Great Wall's existence might be linked to the mysterious influence of dark energy. This enigmatic force is believed to be responsible for the accelerating expansion of the universe, but its exact nature remains unknown. Some researchers speculate that dark energy might not be a uniform force but instead vary across different regions of space. If this is true, then certain areas of the universe, such as the region containing the Great Wall, might have experienced different rates of expansion, allowing structures of this scale to form in ways that standard models cannot explain. There is also the question of what lies beyond the observable universe. Because light takes time to travel, we can only see objects that are within a certain distance from us. Beyond that, the light from distant galaxies has not had enough time to reach us. But if the Great Wall extends beyond this cosmic horizon, then we may never be able to see its full extent. It could be part of an even larger formation, one that stretches into the unknown, forever beyond our reach. Some scientists speculate that if we could observe the universe from a vantage point outside our current observational limits, we might see patterns far more intricate and structured than we currently imagine. It is even possible that the Great Wall is just one of many such structures, forming a cosmic lattice that extends across the entire universe. Another possibility, one that is both fascinating and unsettling, is that the existence of such a massive structure suggests that the universe is not as random as we once believed. If the Great Wall follows a specific pattern or structure, then it could imply that the universe itself has underlying rules that we have yet to discover. What if the large-scale structure of the cosmos is governed by hidden physical laws, ones that dictate the arrangement of galaxies, clusters, and walls on an unimaginable scale? One of the more speculative ideas is that the Great Wall might be connected to the idea of a multiverse. If multiple universes exist, then it is possible that the structure we see is merely a boundary, a dividing line between our universe and another. Could it be that the Great Wall is not just a massive collection of galaxies, but something even more profound, a physical manifestation of the boundary between different regions of reality? If such a hypothesis were true, it would challenge everything we think we know about the universe. It would suggest that the cosmos is far more complex than a single, isolated entity, and that our universe might be part of a much larger multiversal structure. The implications of this idea are staggering, as it could mean that the laws of physics themselves vary from one region to another, and that what we perceive as the universe is merely a tiny fragment of a much greater, incomprehensible whole. Despite all these theories, the Hercules-Corona Borealis Great Wall remains one of the greatest unsolved mysteries of modern astrophysics. It is a cosmic enigma, a structure so vast and so perplexing that it defies easy explanation. Whether it is a natural feature of the universe, a relic from a past cosmic cycle, or something even stranger, one thing is certain: it has changed the way we think about the cosmos. As we continue to push the boundaries of our understanding, we must confront the fact that we are still only at the beginning of our journey into the unknown. The universe is a vast and mysterious place, filled with structures and phenomena that challenge our theories and force us to rethink our assumptions. And as we build more powerful telescopes, refine our models, and explore new frontiers of science, we may one day uncover the true nature of the Hercules-Corona Borealis Great Wall. But until that day comes, it remains one of the greatest cosmic mysteries, a testament to the boundless complexity of the universe and a reminder that there is still so much left to discover. And perhaps, in the distant future, when humanity has ventured further into the cosmos and unlocked more of its secrets, we will finally understand the true significance of this colossal structure. Until then, the Great Wall stands as a monument to the unknown, an ever-present question mark in the vast expanse of space. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.